opportunity to talk to folks here at NCAR. And then after the long break, we'll come back for a lecture on climate variability from Clara. And then Jesse will talk about the introduction to lab. Today's lab is about diagnostics, which is kind of a breakout lab. We'll talk a bit more in a few seconds. And then on the launch activities, again, we have a Mesa Lab private tour today. And again, Jesse will be leading it. It will be super fun, so I encourage you to attend. And the meet a scientist, again, if we have vacancies, I think you can still find, for example, Teresa on the table outside to fill out your name. Then afternoon, we have lectures on land ice modeling, and then paleoclimate, and then lab exercise again. And for the diagnostic lab today, you will notice in the diagnostic chapter, you have this different component: atmosphere, land, ocean, sea ice, qubit. So you could choose one of your favorite topic. I would choose, for example, I'm interested in ocean. I would do ocean, and I would do qubit. And I would also browse the additional topics. Right from here, you have post-processing, CVDP, CSM analysis tools, ADF, and UX array, which are all very useful resources. So, because this is kind of a breakout diagnostics, you could, take a look at what it is and manage your time accordingly. And of course, you can always do labs of other component when you go back to your own institute. I believe the documentation is clear enough that you can go through it on your own without any help. All right. So that's the lab today. And I was asked to send you another survey about the computing NCAR scientific computing system. So this is made by Brian and Eric. Basically, it's questions about your experience using the NCAR HPC and the Jupyter Hub. Later we will use this afternoon. So you have plenty of time to fill this out. It only takes about 5 minutes. You can do this while you're here before Friday, or maybe you can take it back to your home institute if you don't have time this week. So yeah, it's another favor I have to ask. Okay. So that's just a brief logistics introduction for today. Any questions so far? Yes, Elizabeth will send you the link of the computing survey. Yeah, okay. Sounds great. I think we can get an early start today, now that we're all here. Let's see.
So can I put it, let's see. Okay, I've got my timer starting here, so I keep to a bit of time. All right, good morning. My name's Rebecca Buckholtz. I'm a project scientist here at the Atmospheric Chemistry Observations and Modelling Laboratory here at NSF NCAR, and I'm going to talk to you about chemistry this morning, one of my favorite things to talk about. I want to first acknowledge all the people who have contributed to these slides. The model is quite a large model, and there's a lot of knowledge here that not just one person can know about. So thank you to those people. I'm the Chemistry Climate Working Group Liaison together with Sean Honemichael, and there are other co-chairs, Simone Tilms and Rafael Fernandez, and our software engineer is Francis Beard. So the first thing I wanted to say before we really get into it is there's a lot of information that's going to come to you this morning, and I know there's a range of experience here in the room. So think of it as the first step to understanding chemistry, atmospheric chemistry in the model, and you might need to come back to these slides, look at the references in a little bit more detail, and just think of it as like this is the first point of information for you. This is the outline of what we're going to do today. So what I'm going to talk about this morning. So I'll talk about motivation, about why we want to look at atmospheric chemistry. Then there's a large section of adding it, all the different components of adding atmospheric chemistry into an Earth system model like CESM. If we have time, I'll go through a couple of applications, how you might want to use atmospheric chemistry, and then leave you with some support details on getting more information. This is a really nice picture on the right here that I like to show how complicated atmospheric chemistry is. We have lots of different sources, both natural and anthropogenic, and we also have a lot of different processes happening in the atmosphere: transport, cloud processes, chemical processes, and different layers of the atmosphere, troposphere and stratosphere that are shown here. Okay, so motivation. Atmospheric chemistry is important for a few different reasons. The first one I'll talk about is health. So ozone, while it's good for us in the stratosphere, it protects us from UV radiation. At the surface and in the troposphere, it's harmful to human health and vegetation. It can cause damage to tissues, causes inflammation, and increase asthma symptoms, for example. The other chemical constituent that we're concerned about in terms of health is particulate matter. PM 2.5 is the one that's particularly concerning for health. It means it's smaller than 2.5 microns, and it can be breathed really deep into the lungs, and it's hard to get out of the lungs. It causes cardiovascular impacts. And there are lots of different sources of these kinds of constituents, both anthropogenic and natural as well. So atmospheric chemistry related to air quality is predicted to cause 7 million premature deaths from the WHO. Another reason that atmospheric chemistry is important is because it has impacts on climate. We all know about carbon dioxide. There are other short-lived trace gases that are climate relevant. We also have methane, ozone, water, and then those aerosols, that particulate matter, can also have climate impacts. And it's really important to describe the ozone and aerosol precursors and also those aerosol cloud interactions in models, because aerosols are really, from this image on the right here, you can see that there's a lot of uncertainty in the aerosol component of the climate impact. And then the final point I wanted to touch on in terms of motivation is the stratospheric ozone. So ozone is good in the stratosphere. It protects us from UV. And we had the ozone hole that was occurring, started around the 1980s-ish. And so modelling the ozone hole recovery, predicting when that's going to happen, is something that atmospheric chemistry models can help us with. And also pinpointing things of any slowing trend in the ozone hole recovery can be helped by atmospheric modelling. Okay, so those are some motivation slides for why we want to look at atmospheric chemistry. Now we'll get into the processes that we really need to consider when we're thinking about it. So if we think about a box of air in front of us, any chemical, chi, I called it chi here, any chemical in front of us is really a determination of the sources of that chemical and the sinks, so the sources and the loss of that chemical. And we can break that down into a complicated equation, and we're going to go through this equation one by one to talk about each part of the sources and sinks of chemistry in the atmosphere. So here's the little box on the right-hand side with this chemical chi, and the first aspect we're going to talk about is emissions. So in CESM, there are 4 main types of emissions of chemical constituents. We have, and aerosols as well. We have surface emissions, so these are prescribed fields that are read into the model, and these can be anthropogenic, biogenic, biomass burning, ocean and soil emissions. We have similar prescribed emissions that have a vertical component, so this would be aircraft emissions, volcanic emissions that have an altitude where the maximum emission is located. We also have interactive emission constituents as well, so we have interaction between different components of the model, the community Earth system model. So we might have the land component giving information to a dust module that gives you dust emissions into the model. And we'll go a little bit more into detail to show you an example of that. And there are other components as well that are interactive. And then the other thing we have are surface concentrations that are lower boundary conditions. And these are for more longer-lived species such as CO2 and methane. And these in the bottom right here are an example of those lower boundary conditions that are prescribed in the model as well. And they're important to understand radiative conditions. So an example of the interactive emissions regarding dust, this shows the parameterization up the top there. On the left is the original default parameterization, and we're moving towards a newer parameterization developed by Denny Long in 2023. And he's added some more variables there that are important for creating dust emissions interactively in the model. And in the middle there are the results from the new dust module, and we can see they compare much better with observations on the right as compared to the original. Another interactive emission module that we have in CESM is biogenic. So this is emissions directly from vegetation. And that depends on a whole bunch of emission factors as well as LAI, leaf area index, which you can get from the model as well, and plant functional type. Okay, so that's looking at emissions. Now, the next step I wanted to look at was chemical production and chemical loss. So there are chemicals and aspects and aerosols in the atmosphere that are chemically produced. For example, ozone is not emitted directly. You need to have chemistry to get ozone correct in the atmosphere in a model, and ozone is really important, as I said, for health. So we need to understand the chemical production and chemical loss of certain atmospheric constituents. So I added in this image here to show in the troposphere how complicated chemistry can be. We have on the right here, on the left here, the non-methane volatile organic compounds. That's actually a whole class of compounds. It can contain hundreds of compounds of carbon-containing molecules, and we're saying they all go into this hydroxyl radical loss, this chemical reaction with the hydroxyl radical, to start a chemical process. We also show here the NO-NO2 cycle, the nitrogen cycle, nitrogen oxide cycle, which is the main way of producing ozone in the troposphere. And so really, this is a really complicated picture of a summarized chemistry mechanism in the troposphere. And we have a lot of processes going on. We need to think about photochemistry. Light is really important for chemistry in the atmosphere, and there's different chemistry that happens during the day and during the night. We think about gas phase chemistry, heterogeneous chemistry, aqueous phase chemistry, and then gas to aerosol exchange as well. So in the stratosphere, the chemistry is a little different. We have the main aspect that we're thinking about in the stratosphere is that ozone hole, the ozone loss for the ozone hole, and then the ozone hole recovery. And so halogens are really important in the stratosphere in terms of ozone loss. So we need to make sure we represent that correctly in the stratosphere. And then just to show you a summary of the type of chemistry we have in CESM right now, when we're thinking about all these chemical constituents and aerosols in the atmosphere, when we're putting them into a global 3D model, we have to have a balance between representing chemistry comprehensively and actually being able to run the model in a timely manner. So there's a cost balance consideration thinking about chemistry. So you can see the different number of constituents that we have in the table on the right-hand side. We also have on the left-hand side here a bar chart showing different number of compounds in the different chemical mechanisms. And so we have complex chemical mechanisms on the left going to simplified mechanisms on the right. And our default mechanism in CESM is the T1S mechanism. So that's tropospheric chemistry, the mechanism 1, and stratospheric chemistry. Depending on what your what your experiment is, what your question is. You may want to use a simplified chemistry such as T4S, which is, when we look at the bar chart, it's this one here. It has a little bit less chemistry in it, but still enough to understand chemistry happening in the model. And you might want to use something like this if you're looking at 100-of-year runs or something like CMEP7 simulations, doing a little bit simplified chemistry in order to have longer runs. And then I also wanted to touch on, even if you don't have a chemical mechanism, you still need to have chemistry in the model for climate simulations. So the way this is done is we run a full coupled simulation of chemistry, save out oxidants, and then we can prescribe those. We can read those back into a climate run of the model. And this is important because if we look at this list down here, prescribed ozone is used for radiative calculations. So it has a radiative effect. We need to understand how ozone impacts any climate response. Oxidants are also used for aerosol formation, and aerosols are important for clouds and also radiative impacts. Methane oxidation, stratospheric aerosols, nitrogen deposition, and secondary organic aerosols. We still need those in a climate scale simulation. So I talked about chemistry a lot. We also have representation of aerosols in the model. And so this is a simplified representation of as well. The main way we do that is to use the MEM4 module, which is a 4-mode bin aerosol model. We have the A1, just by definition, is the accumulation mode of aerosols. Oh, sorry, I didn't mean to move on. A2 is the Aitken mode, and the coarse mode is A3, and we have this 4th mode, the primary carbon, as well. So these are the main aerosol representation, and then we also have secondary organic aerosols as well. So when you have sticky molecules being emitted into the atmosphere, sticky chemicals, they can stick together and coagulate and create secondary organic aerosols. And so that's what we have also in the model. We have a simplified version of representing that, and we also have a more comprehensive version of representing that with the VBS, volatility bin set, with 5 volatility bins. Okay, so that was a pretty intense aerosol chemistry discussion. The next thing I wanted to touch on was the advection and diffusion, and this is really determined by the model, the CESM model, the physics in the model, the transport that's happening in the model. And I wanted to mention both free running and nudged versions. So free running model means you're using all the physics and dynamics in the model to tell you where constituents go in the atmosphere. If you use a nudged version, then you're nudging things like temperature and U and V, wind directions, to a reanalysis. So a reanalysis is a data assimilation of observations. So you're really nudging your model towards what really happened in terms of winds and temperature. And this can be important if you're looking to reproduce, say, a field campaign of air quality measurements. So depending on your question, you may want to use free running or nudged version of the model. And just a reminder, there are different dynamical cores in CESM, and so these will give you different kinds of dynamics, and there may be different transport happening between these different types of dynamical cores. In particular, MPAS has the capability to do non-hydrostatic transport, and so that's really interesting if you're looking at probably below about 7 kilometres. That's kind of the way forward below 7 kilometres right now. Okay, and then finally what we have to talk about in terms of this little box with our atmospheric chemistry coming in and out is deposition, and we have both wet deposition and dry deposition. So wet deposition follows generally a first order loss process by this equation here, looking at this is looking at like clouds and precipitation in an actual grid box of your model. I wanted to shout out to Danny Murray, who's recently evaluated wet deposition in the model and found it's not doing too badly. So the other thing I wanted to point out is how complicated aerosol cloud interactions are in terms of wet deposition. And so I wanted to just leave this slide up for you to look at later in terms of looking at, in-cloud scavenging versus external cloud scavenging, activation of clouds, all of that kind of stuff. And then finally, we have dry deposition. So when air goes over a surface, there'll be things deposited on surfaces just through dry deposition. And this is determined by a resistance model as defined here. Okay, so that's the summary of everything that we have to represent in a global CESM model regarding atmospheric chemistry. And thinking about that for hundreds of species, as we saw earlier, in every grid box, at every time point, for a very large model can get very expensive very fast. So again, just reiterating that, thinking about what chemistry you need to answer the question you're asking. Okay, then I wanted to just touch on a couple of questions. Oh, sorry. I wanted to just touch on a couple of examples of how we use atmospheric chemistry in CESM. This first one is using the regional refined capability of the spectral element dicore. And so we have 14 kilometers over the contiguous US and then 100 kilometers elsewhere. And on the left in the video here, we have the global 1 degree model, so no regional refinement. And on the right, we have regional refinement over the contiguous US. And we can see there are differences in ozone modeled by these two different model simulations. They're using the same emissions, they're using the same model in terms of the physics. It's just the regional refinement gives you a different result here. And so that's really important to think about fine-scale impacts of air quality. And we can regional refine this grid over any part of the Earth that you, as a user, would like to look at. So that's something that a user could define in terms of the regional refinement. And then the other application I wanted to mention was this chemistry-climate interaction. So we looked at the impact of aerosols from the Australian wildfires in 2019-2020 and how they impacted the climate. And we used CESM to show that there was cooling over the Pacific Ocean and that the Nino 3.4 was much, it was more in a La Nina state with the fires than without the fires. So the Australian fires potentially increased the likelihood of that La Nina happening. Okay, so I'm just perfectly at time here. I was just going to leave you with a few notes on user support. We have a wiki page for chemistry in the model linked at the top. The best place to ask questions first is we have a forum page, and so that's really important to search for any questions you have. Somebody might have already answered a question you have, and you can also ask new questions. We have contact details if you need to send emails, and we also have a regional refinement wiki to give you more details about that. I also wanted to highlight at the bottom of the wiki page for chemistry, there's this CAM documentation, which is really useful to learn about the model more. And I think that was the main thing I wanted to highlight there. And so just to have some final thoughts, some key takeaways is atmospheric chemistry is important in global models because it has impacts on health, weather, and climate. This is a summary of how we need to parameterize and approximate a lot of different aspects of atmospheric chemistry. And then models are really useful because they allow us to perform multiple experiments that we can't do in the atmosphere. We can do them in a model. And using that correct model or configuration of the model for your particular question is really important to think about. And with that, I think I've left enough time to have some questions about atmospheric chemistry, but thanks for your attention.
Questions for Rebecca? Yeah.
Hi,
thank you. I have a question about the regional refinement that you explained. Between the high resolution and the low resolution over a particular area, is the transport and chemistry still the same in areas that aren't buried in the grid?
Yes, yeah.
Yeah?
Yeah, absolutely. So this is all running in line at the same time. So we have here, for example, we have a gradient from 14 kilometres to 100 kilometres, and these grid boxes here will transport atmospheric constituents between the different grid boxes in time. It's not like you have to nest a grid and then run one and then run the next and run the next.
Okay.
That answer your
question? Yeah, it does. Thank you.
Thank you for a great overview. I feel related to the regional refinement, the musical scheme, is it possible to do the regional refinement in a vertical scale, in certain vertical levels instead of the horizontal regional?
That's a really good question. No, I believe we cannot do that yet, but it's something it would be really good because over that that regional refined area, we may want finer scale closer to the surface as well, but we cannot do that yet. What you can do, I think, is you can nudge at different layers of the atmosphere. So that's something interesting that you can do variably, but it's not about the size. We have recently, from CESM 2 to CESM 3, we have increased the vertical layers in the boundary layer and at the UTLS. And so there is more information now than previously, but it's not variable.
When you were showing the improved dust scheme for CSM3, I noticed that it's still, over South and East Asia, it still is maybe not super representative of the observed dust scheme, and I'm wondering if you have any idea why that might be in CSM3 or if there's any particular work that's being done in those areas to improve that.
Yeah. So you're saying over...
We're kind of like South Asia, that Pakistan, northern India.
This area here?
Yeah, and I guess.
Yeah, so in the observations we see a peak in aerosol optical depth. We don't see it here in the dust scheme. Danny would be the best person to ask about this. He's still definitely working on this scheme and getting it running in CSM3 with different configurations. Short answer is I don't know why that's still like that. It could be something to do with surface roughness in the land model needing to be updated. It could be something to do with LAI. But yeah, that's definitely something we're still looking into, and Danny's still here improving this model.
Is there in the atmospheric chemistry, is there any interactions between the dust and atmospheric aerosols? Or sorry, anthropogenic aerosols?
Do you mean mixing of the dust getting coagulated into?
Yeah, encoding.
Encoding? I am not sure. Do you know that answer, Mijong? I think that seems a little bit more complicated than what we have in the model. Yeah, we would have to talk to an aerosol expert about that, but let's connect afterwards and I can connect you with some aerosol experts if you're interested.
Thank you so much.
Hi, thank you. I liked your explanation of nudging. I've heard about it a lot, obviously, to model certain events or time periods. And I was wondering, just in this kind of equation, you went through all the variables, what that actually translates into, if there's known values to solve for each of these, and then in the just free running, it's just unknowns, or how that actually works within the model.
Yeah, so in the model, you will have fields of temperature and then U and V as well. And so what the model does is when it's a nudging situation, it is taking those fields that gets calculated and saying, comparing them to a reanalysis. So you read in a field of data from a reanalysis like MERA2 is one that we use from NASA. MERA2, they assimilate data from satellite measurements and other sources of TU and V, and they assimilate it into their model and create a reanalysis. And then that reanalysis gets read into this model, and nudging means you don't completely take that value and overlay your model value, your CESM value with that. You just say, okay, this is a certain amount off. I'm just going to move it towards what I saw in that reanalysis. And you can change that strength of moving it towards that reanalysis value.
Thank you, that's like the most clear explanation I've heard of it.
I was wondering, like, does like, so among like different regional refinement schemes, so which one do you think is the best? Or it depends on the problem?
What do you mean in terms of different regional refinement schemes? Do you mean like MPAS versus spectral element, or?
Yeah, so like how it's refined, like in terms of like the spatial structure.
I think it depends on your question. So in terms of the spectral element refinement, which is the top right picture here, that is with a hydrostatic core, and so we really cannot go below about 7 kilometers. That's pushing the skill of the physics to represent clouds and convection, right? So for the case of if you're happy with a 7 kilometer grid, definitely use spectral element. That's been well tested. It's been kind of scientifically used in the community. If you want to go below, we're experimentally using MPAS, and so that can go down to 1 kilometer right now. I think they're trying it at 3 kilometers with chemistry, and so if you want to look at really fine scales, MPAS is probably the way to go. I have also heard that in spectral element, they're considering having a non-hydrostatic version of that in the model, but that's very new in terms of talking about that. That might be a way out. Does that answer your question?
Yeah. And also another question is it possible to do like a regional refinement for like and a certain range of latitudes, like a band?
Yes, yeah, absolutely. Actually, that's a really good question. It can add on to your question before. With MPAS right now, we really only have this ability to regional refined over one area. With the spectral element, you could do a regional refined area over CONUS, and then you could go, I also want to do Hawaii, and then I also want to do Asia. And you could do them all separately, and then in between have like 100 kilometers going back down to 100 kilometers. So that's a possibility with spectral element as well. And then you could have a whole latitude band, regional refined, and then outside that 100 kilometers. It's user defined with spectral element.
So with like the comparison of the wet deposition and that it's performing well, but like if it weren't, how would you be able to tell the difference between what is an issue with the chemistry versus like if you're thinking of processes that involve convection or clouds? Like how do you know if it's a chemistry issue or a representation of clouds or other things that are in the atmospheric model?
Yeah, that's a good question. Danny also compared precipitation in the model, the two observations of precipitation. And so that was the start of the question as well, are we getting wet deposition correct for the right reasons? Or is there something else going on? And what she also did was filter out her wet deposition in the model to be where the precipitation was correct. And so where we have correct precipitation in the model, then we're evaluating the wet deposition. She didn't really look into where we have precipitation incorrect. I think that's a different question in terms of chemistry, but that's information that we can also give back to the rest of the team. But yeah, it's a complicated process because is wet deposition not correct because your emissions aren't correct and you're not having enough chemistry in the atmosphere? Is it because there's not enough emissions or they're just not in the right position to get transported to the right place? Is there not enough precipitation? Are there not enough clouds? Like there's a big question there. So we tried to adjust for that with looking at precipitation, but there's more to do for sure. Thanks.
Yeah. Any other questions? Perfect timing. Okay. Thank you, Rebecca.
Cool.
now it's time for photo. Let me confirm you're gonna take your photo. Take the photo right outside. welcome Mijong to give us a talk on WACCM, the high top configuration of CESM.
Thank you, Hui. So good morning, everyone. I'm Mi-jung Park, and I'm at ACOM, just like Rebecca. And I'm working on WACCM specifically. And today, let me introduce you to WACCM, the high-top configuration of CSM. First of all, I'd like to thank Nick, Mike, and Doug for letting me use some of their material from the talks they have given in the past. Actually, I stole them, so. So it was winter of 1999. There were two breaking news on UCAR quarterly newsletter. First one says, it's about time, a new upper atmosphere model. So you're looking at this black and white photo. There are three scientists. One is Byron Boville from CGD. In the middle is Rolando Garcia from ACD. Now it's ACOM. And the third person is Ray Roble from HAL. And the second breaking news was Mozart, an uncompromising global model. And I put Doug specifically, but there are multiple people here. Many of them were scientists at ACD. So what did they say? First one was, a year from now, we expect to have a model that extends from the surface to 120 kilometers and includes ozone chemistry. That's exciting. And the second, a new version of NCAR's global chemistry model is about to give atmospheric scientists a better look at the global budget and interactions of ozone and almost 50 other chemical species in the troposphere. So sadly, Byron Boville passed away about 20 years ago. And this is a newsletter from University of Washington, published in 2006. But in it, so he was a leader in the development of CCSM at the time, is community climate system model. And I was fascinated by finding this quote. He said the whole atmosphere community climate model has to be pronounced as WACCM. And this picture is actually from just yesterday. Doug and myself and Rolando, we're laughing about something. I'm sure Rolando said something funny. I don't remember what it was, but I'm really grateful to work with them still. They're around to help us with this amazing model. So I wanted to tell everyone, WACCM didn't fall from the sky. There's rich history of all the scientists gather, okay, we need this model, so we have it. So now let's look at the motivation for WACCM. So there are multiple atmospheric phenomena as you can think of. Let's put all of them into a two-dimensional space, as you can see from the figure on the left. For this one is x-axis is time, from very short time scale to long time scale, like centuries. And the y-axis is spatial scale, small scale to large scale, like global scale. And if you think about the middle atmosphere, which includes stratosphere and mesosphere, it couples surface and lower atmosphere to the upper atmosphere and space. And you can think of many phenomena between these places. And in middle atmosphere, it connects or couples the lower atmosphere to upper atmosphere. So we need a model that can simulate this coupling on short time scale, such as weather or subseasonal to seasonal forecasting, or long time scale, like climate and paleoclimate time scale. So when you look at the vertical structure of the atmosphere, it's even more clear. So this figure is from a little bit old, in 2001, published by Jarvis. And from the bottom, you go up, okay, there's a troposphere from 0 to 15 kilometer, and there's stratosphere, 15 to 50 kilometer. And above that, there's something called mesosphere and lower summersphere. We call it MLT region. It's between 50 to 150 kilometers. This is important. And if you go above, it's geosphere, ionosphere, and the sun. As you can see from this figure, in MLT region, the energy is coming down from above, and energy is going up from below. And its interaction between these energies is important. And one example, as you can see this wiggly arrow, gravity waves are important. It's generated in the troposphere and lower atmosphere, transfer upward, and breaks in mesosphere. So in this article, it says the MLT is an important link in the vertical transfer of energy and is most sensitive to the sensitive indicator of global temperature change. Oh, we didn't really know that. And one thing this article also mentioned is that the WACCM at NCAR was an ambitious modeling initiative. So we're lucky to have this model. So now let's revisit. So CESM has atmospheric component. One is CAM. CAM is low top model. It goes only up to 42 kilometers. And WACCM goes up to 140 kilometers. And above, there's WACCM X. So this is a figure showing all the components of CSM, but this one I just chose for CSM3. This is our future version of CSM. So couple in the center, and if you look at the atmosphere component, we have CAM, low top, and WACCM, high top, and WACCM X, and CAM, so Rebecca just went through. So with CSM3, CAM will become 7, WACCM will be WACCM 7. For WACCM X, we're thinking of calling it WACCM 7X, but it's not final. We're still talking about it. So I mentioned to you briefly about gravity waves. So gravity wave physics is important in middle atmosphere, so in WACCM, because in the atmosphere there are various scale, wide range of gravity wave spatial scale, but some of them, actually a large portion of them has too small of a scale that can fit in the grid size. So what we do, we have to parameterize gravity waves. And parameterization can introduce us a big uncertainty. And there are 3 primary gravity wave schemes. First one is orographic gravity waves. It affects the stratospheric polar vortex, for example. And second one is frontal gravity wave. It's affecting polar vortex and mesopause region. And the third one is really important, convective gravity wave. It's important for the QBO and the mesopause region. So now, okay, we know there's WACCM, and how is it different from CAM? Is it only the vertical extent? So let me go through all this list to give you an idea what are the differences between WACCM and CAM. So WACCM, we inherit the dicore, dynamical core, and physics from CAM. So they changed something and gave it to us. Hey, what did you guys change? I don't know. And like, QPO looks different, huh? And that's our interaction. So WACCM goes up to 140 kilometers. In WACCM 6, we have 70 or 110 vertical levels. But for WACCM 7, we are going to have 135 vertical levels, way more. And for chemistry, I just listed 2 chemistry modules here. One is middle atmosphere. As the name suggests, we're only interested in middle atmosphere. We don't care about troposphere. So making tropospheric chemistry a little bit simpler. And there's another one, TSMLT. So it means troposphere, stratosphere, mesosphere, and lower thermosphere. But this is based on CSM2, WACCM 6. This is a little bit confusing with Rebecca's talk. She showed everything based on newer version of the model. But the basic idea is you choose how complicated chemistry you want in troposphere or mesosphere or even high up. That's the basic idea. There are other things. We have prognostic stratospheric aerosols and ion chemistry and LTE and gravity wave drag. So you can read through. We can go back to this PowerPoint and later read through, These are the differences between WACCM and CAM. So there are more differences between these two models, not just the high top, because if you go up high, we need more things put into the model for the model to work properly. And at the bottom, you see WACCM X. So WACCM X is a model of the entire atmosphere that extends into the thermosphere to 500 or 700 kilometers. The top is not fixed because it depends on the ion activity or solar activity. I don't know much about, so it says 500 to 700 kilometers. Because it includes ionosphere and thermosphere, it is influenced by high up from space weather and influenced by from low altitude. If you want to learn more about it, go to this website and read about it. You might be an expert already in high altitude dynamics. So this time, okay, there's WACCM. Now there's WACCM X. What are the differences? So biggest difference is WACCM goes up to 140 kilometers and WACCM X goes up to way high up. But there are a couple more differences also. WACCM X is much more expensive to run because the time step is only 5 minutes compared to half an hour for WACCM. And WACCM X, we can only run 2-degree configuration. For WACCM, you can do either 1-degree or 2-degree configuration. And for WACCM X, we have more simpler chemistry because we don't care about too much in lower altitude chemistry. So we can learn about it, go to website, GitHub we have all the documentation that Rebecca showed. Rebecca's PowerPoint has all the good resources. Now, we're ready to run WACCM. Okay, how do we start? So WACCM is atmospheric component. So you need other component, ocean, land, and sea ice. And you can choose either, okay, I want ocean to be interactive. That means free running. Or I want ocean to be just data ocean. So you can either choose observations or climatology. For atmosphere part, it's the same idea. You can either run it as free running, model is free running, or it used to be called specified dynamics, which means I want dynamics to be just as it is like real atmosphere. Now we are going to call it nudging approach, as Rebecca explained. When I think of a nudge, I feel like I'm elbowing someone, hey, just move over. So nudging can you can put it 5% nudging, 10%, 50, or 100%. So this is really useful. If you have specified dynamics or nudging approach, you can compare it with satellite observation, for example. I want to look at water vapor from satellite comparing to CSM or WACCM. This is a good approach. And another one is called specified chemistry. I don't care about chemistry much. Then use a specified, simpler chemistry and run the model. This is up to you. You choose whatever fits to your research goal. So, excuse me. So now right now, CSM WACCM 3, WACCM 7 is not out yet. If you want to run WACCM, you have to use WACCM 6. You run any model, we prepare for you, it's called ComSet, component set. As I said, okay, I want atmosphere interactive or ocean and land. So these are already scientifically supported, tested. You go to website, okay, I want this ComSet. So there are 5 listed here. They all start with F. So F ComSet means atmosphere is fully active standalone. And 1850, for example, is pre-industrial, or F09 is 1-degree resolution. So you can learn about the name of the ComSet, and you choose which ComSet you want to use. And it all has W in it. It means WACCM, FW1850. So you get the ComSet name, oh, okay, this is what I want to use. And with this ComSet, you also have to choose chemistry module. How much chemistry do you want? So I told you the basic idea is you want really complicated chemistry or a little bit simplified chemistry. These names are based on WACCM 6, CSM 2. So this is what you see if you go to the website now. But in the future, if we move to CSM 3, you will see slightly different names, which Rebecca showed in her talk. But just remember, oh, just decide and read about the description and how many, so you can see how many species in this. In long time ago, 1999, we thought 50 is a lot. Now we have so many species. This is really exciting. And for WACCM, same thing. We have counted, scientifically tested. You guys can go ahead and use it. And now, okay, we learned about WACCM, okay? I understand what WACCM is. I can run it. And what do we do with WACCM? I want to do stratospheric dynamics study or chemistry study. So one thing is really important, in my opinion, in the stratosphere is stratospheric quasi-biennial oscillation. Some of you might be familiar with, some of you are not. But QBO, as you can see, it's not quite biennial. It's quasi-biennial in the stratosphere and tropical lower stratosphere. The wind direction changes about 2 years from easterly to westerly. So you might think, maybe it's just important in the tropics, but no. QBO can affect polar vortex, and this is a really important phenomenon in the stratosphere. So for models, do stratosphere or middle atmosphere, we have to get the QBO right. Then without right QBO, we cannot trust anything else. So we try to make the QBO look right. So you're looking at two plots. The bottom figure is from WACCM 670 level. This is the scientifically tested version. You can run 70 level. But we look at the QBO. The purple and green is westerly and easterly alternating. There is QBO, but doesn't look that perfect because the purple area is westerly. It's not coming down low enough. So what do we do? So what they did, what we thought, I didn't do it, but what we did, it was, so adding more vertical layers in the upper troposphere, lower stratosphere, really improved the QBO. So top one is WACCM with 110 level version. So QBO looks great. So now with this model, you can study QBO and other things. But it is important to understand how the QBO looks in the model. Actually, we're working on with this new version of WACCM, and you have to tune until you get the perfect QBO. We're not there yet. And some of you might feel like, you know what, I want to look at water vapor in the stratosphere. Okay, you can look at water vapor. And another feature is important in stratospheric water vapor is tape recorder. Tape recorder sound might be, for some of you, okay, I know what it is. Many of you like, what is it? You never see it. So this low water vapor, high water vapor transported upward every year. Winter is dry, summer is wetter. So we look at, it's called stratospheric water vapor tape recorder. So we look at this feature in WACCM too. But there was this really extreme event. It's called Honga Tonga volcanic eruption in January of 2022. It injected so much water vapor in the stratosphere. I want to study this volcanic eruption in WACCM. How do we do it? We have to have, so top figure is from satellite. NASA has a satellite called Microwave Limb Sounder. It was launched in 2004. Actually, it has over 20 years of record. But as you can see at the very late part, the satellite is not doing well, so data is not perfect, but it might die soon. But it's a really good satellite. You can water vapor. Okay, there is high water vapor in 2022 related to this volcanic eruption. Can I use WACCM to look at this? And then maybe this water vapor is changing circulation or radiation or ozone? You can. So my colleague June did this run, but we don't have more outputs here. But for this case, because you want to compare with satellite data, you use SD run, specified dynamics run. This is exciting. There are not many models can do this other than WACCM. So now I'm going to show you some of the examples. So how do people use WACCM and WACCM-X? WACCM and WACCM-X is more expensive than Northrop model. But if you think about the atmosphere doesn't end at 40 kilometers. or 60 kilometer or 80 kilometer. It goes forever. So in a perfect world, we want to have this really, really high top model, but it's maybe not practical. So we have to choose, do I want WACCM or WACCM-X? This is not really too recent research, but I think this is showing us a really great idea how the atmosphere is all connected. So title of this is just article on EOS, how sudden stratospheric warming affects the whole atmosphere. So you've heard of SSW, sudden stratospheric warming, affecting stratosphere between 10 to 50 kilometers, but it doesn't end there. So this, depending on how SSW works, the temperature and chemistry and ionic activity in the high altitude changes. And I was actually talking to Nick about this, and he said, it took a long time to make this figure. And this is such a great figure, I love it. So I wanted to share with you today. And now I have a couple of papers that use either WACCM or WACCM-X. I just chose this based on, okay, I look at the title and it looks interesting. It was published either this year or last year. The first one was these people looked at recent lower stratospheric ozone trend in CCMI 2022. CCMI 2022 is multiple model initiative. They compare different models and they compare ozone trend. If some of you are interested, oh, I want to look at ozone trend. Okay, we can use WACCM. So the way I put these slides from this page on is you can go to my talk and look at this and click this link with a paper if you're interested. Yeah. And I'm going to go over quickly because he was oh, time. Okay. And the second one is rhodopsin circulation by Natalia in 2025. And the third one is impact of upward propagating diurnal tides is WACCM-X. And the other one is looking at some chemistry. This is done by Jun Zhang and ACOM at GRL. And this is the last paper. There are so many papers using WACCM and WACCM-X. I want you to go explore it. Now, my last slide. Maybe not last slide. So what do you want to do now? So we have this amazing model coupling lower atmosphere and upper atmosphere. We have comprehensive chemistry, aerosol, and you decide what kind of research you want to do with model. And this WACCM is truly a collaborative work. ACOM, CGD, and HAO within NCAR and the wider community. So we work together. So I'm happy to get your input or you know collaborate. Just let me know. So this is the last slide. And questions, as Rebecca said, go to this discussion forum. This is really useful, and I'm happy to answer your questions, either email or ask me. So thank you for your attention.
Okay, questions for Bijan? Yeah.
With WACCM versus WACCM-X and the time step, why is it that there needs to be a 5-minute time step for WACCM-X?
So if I can answer this, so model time step is important for physics and dynamics. They have to fit every step. And if time step is too long, model becomes unstable. And because the waves generated, they break. So we have to reduce the time step to make it work. In my understanding, I'm not an expert in this. I think WACCM-X can be really unstable with such high tops. So you have to have really small time step to make it work. Great question.
From the slides you showed, the 70 level WACCM doesn't get the QBO down to 100 millibar. Do you advise us to still use the 70 level to study stratosphere internal variability, or do you advise we use the 110 level?
So I can answer to that question in a different way. So this WACCM 670 level is going away. We're moving to a new model. But if you really want to use that now, so you have to be aware. Okay, I'm not going to look at the QBO specifically because I know QBO doesn't come down low enough. But if you want to look at something else, a little bit higher altitude, but as long as you keep in mind the fact that QBO doesn't come down low enough, so don't use it for really low altitude looking at QBO, but you can use it for other other research. But since we're working on new version of the model, or you can ask us, hey, can I use 110 level version? It's not public, but we can work together to get that for you.
Thank you very much.
And my question is like a follow-up to his own question. Besides the QBO, what other large-scale atmospheric teleconnections does the WACCM model account for, like ENSO, MJO, or other stuff like that? Or is it just QBO focused?
No, I think so. If you look at, I think atmosphere is really fascinating and it's really complicated. So WACCM does have MJO, other ENSO and everything, but the focus is in the stratosphere and above. So you don't want to look at MJO from WACCM. If you want to look at MJO, you can. But ENSO, MJO, QBO, because they're all convection generated and wave, they're all related. For example, you want to look at, hey, how MJO connects to some feature in the stratosphere. That part is really difficult right now because models don't get MJO perfect, and they don't get MJO connection to other species perfect. So not advice, I think it's important to understand what is it that you want to look at and read a bunch of papers. Do they get it right or what is it? Then you get an idea, oh, okay, I have to be careful using WACCM to look at MJO, but WACCM has everything, and chemistry also. Great question. More question?
Thank you, Vivian. Sort of follow up with that and to your comments just now. Doesn't it mean like if we want to, for example, you show the Hunga-Tonga case, if we want to look at the Hunga-Tonga impacts on the surface climate, is WACCM a good option because it does seem to simulate the stratosphere and mesosphere quite well, and we want to use these very detailed stratospheric and mesospheric like simulation to look at the surface. Is WACCM a good option to do that?
So Yahweh, I'm not a Hunga-Tonga expert either, but for Hunga-Tonga, they injected water right in stratosphere. So the changes are more in the upper altitude than the surface climate. So for Hunga-Tonga impact, WACCM is perfect. So we look at stratosphere and mesosphere. But you're interested, oh, I'm a troposphere person. I want to see what Hunga-Tonga did to the troposphere. Just a different matter. And it's not easy to get Hunga-Tonga right in the model. So it'll be hard to see if anything happening in the troposphere, but it's worth to pursue. You can ask someone expert at NCAR or other people, and they can answer your question better.
Thank you.
Good question.
Yeah, it's just a similar question, but I wonder like what kind of activities in the WACCM, and then that's like having a stratosphere troposphere interactions between. That's a huge plume of the water vapor, but how about the aerosols and other chemical stuff inside of the column of the mass, and then also the spatial time resolution is gonna be how fine it can be captured, or what kind of activities.
I feel like I wish I wasn't the expert, but for Hunga-Tonga, so there are multiple papers published. People are working on this report, especially for Hunga-Tonga. There's AGU special session, a lot of activities going on. But my understanding was this volcanic eruption puts so much water in high altitude, about 50 kilometers, and didn't have much sulfur or aerosol put in the atmosphere. So the impact in atmosphere was mostly this water vapor. And one thing cool about using the model is we can look at the future. Okay, the eruption happened 2022 January. You can just keep running until 10 years. Oh, even after 10 years, there's still water vapor left. Something like that. But I think a lot of people in this room are interested in Hunga-Tonga. So read more papers, and if you ask me a question, I can connect to different people. It's great. Okay, it's almost donut time.
Yes, this is perfect timing. Okay, let's thank Visual again. Outside. We're gonna have like CESM cafe break for half an hour. Everyone be back at 10:15. who will give us a talk on climate variability.
Yes. Good morning, everyone. Good morning. So nice to see all of you. Hui asked if I could just introduce myself, so I will introduce myself. I've been at NCAR for most of my career. It's an awesome place, in large part because of these kinds of activities where we bring in all the younger generation of climate scientists. And it's probably more thrilling for me to see all of you than vice versa. So anyway, really happy to be here. So I only have 20 minutes for the talk, so I'm not going to, say very much. But I just wanted to say what I think a very interesting avenue of research is now. That people are doing, but there's lots more to be done. And that is to try to understand and assess, climate change. We all are familiar with how it changes the slowly varying mean state, but it can also impact the variability about the mean state. And this is a more difficult problem to address because you need a lot of samples of internal variability to really detect any force change. But I'll show you some tools that you're probably already aware of or may not be that can really help with this. So today, so the overall title is Future Changes in Modes, meaning patterns of internal variability. Internal meaning that without any changes in, the sun, orbital forcing, greenhouse gases, just the climate system, because the ocean and the atmosphere and the cryosphere and the land all interact. They produce a lot of variability. So that's what I mean by internal. And for today's talk, I'm going to show you a very tiny application, and that is to the atmospheric circulation over the North Pacific in the wintertime. So this is a case study. This was work led by a former postdoc, J.P. O'Brien, and I think it's just the tip of the iceberg, really, on what you can learn. It's very interesting. Okay, so just setting the big picture stage, if we just think about human influence on climate, and that's primarily coming from well-mixed greenhouse gases, and then, of course, aerosols from industrial activity and from biomass burning, wildfire, and the like. So, of course, changes in the mean state, that's what we're, all the IPCC reports, that's really their bread and butter, is how the mean state has been affected and will be affected in the future. But there's this whole other class of impacts, which is under the category of changes in variability. So you can ask the question, how will the characteristics of these structures or phenomena of internal variability, for example, ENSO, that's one prime example of internal variability, how will that change with climate change? And when I say characteristics, you can think about the spatial patterns. You can think about connections between different parts of the globe. You can think about the amplitude of the variability, the frequency, if there's a preferred time scale. For example, for ENSO, you can think about the impacts. So there's a lot of characteristics of internal variability that could be modified as we continue to pollute our atmosphere. So the toolkit that I think is really helpful right now, and I'm sure machine learning methods are also probably extremely useful for this application. I haven't used them, and I'm not well versed in that. But these initial condition large ensembles, I don't know if that's been covered in the tutorial, but I'll just say a few words about that. So what initial condition large ensembles are, this is where you take a single global coupled climate model like CESM, and you specify the usual, time evolving radiative forcings. So this is the typical IPCC-like CMIP simulations, both historical radiative forcing and future. And then you run many simulations with one climate model and one radiative forcing pathway. And the only difference amongst the simulations is that you have slightly perturbed the initial conditions. And I'm putting this roll of the dice picture here because it really then sparks these different sequences of internal variability. So once you lose the memory of the initial condition, the internal variability will unfold randomly across the different members. So the phase, you can have an El Nino in one member in a particular year, and another member will be a La Nina. So it's completely, spread, a lot of spread then across the simulations due to internal variability that unfolds with a different sequence just because you have tweaked the initial conditions. But then each of the simulations also has the response to the radiative forcing. And then it's all about how to, pull those two apart. So as I said, with this setup, what happens is because of this noise of the internal variability, if you're interested in the mean state changes, this is noise, and you're going to get a range of change in the mean state across the members because the internal variability can also have trends in it. There may not be any physics underlying the trend. It may just be because of stochastic variability, but it can still produce a trend. So that's sort of initial condition large ensembles, we have to be cognizant that we get this range of outcomes. And the real world can take one of those outcomes. But the good part about large ensembles, or another asset, I would say, is that you have, because you've run the model so many times, at each time step, you have all these different realizations of internal variability. So as I mentioned with El Nino and La Nina, at each time step, you have this beautiful sample across the members. And then you can see how the characteristics of, say, ENSO will change. So that's the second bullet point, is what we're leveraging here to address this question about how will the character of internal variability change with climate change. So tool number one is these large ensembles. And then tool number two, which I like a lot, of course, it's not the only tool at all by any means to address this question, but I think it's a very nice direct one to apply to large ensembles. And that's what in the literature, recent literature where it was introduced, it's called snapshot empirical orthogonal function analysis. And I'll tell you what that is, and then you can see why it's such a useful tool. So I don't know how many people here are familiar with EOF analysis. Probably many of you are. Maybe, I don't know if I should take questions now. Is it a quickie? Oh, you were just saying you are familiar. Oh, yeah. So traditional EOF analysis, you have a time series, so you have your observational record, and you want to find spatial patterns that account for, the maximum amount of variance in your data set. So you apply it to a single, your observational record, or in the case of model simulations, a single simulation. And then you get the time series of this pattern. For example, the NAO. That's kind of a typical way to define the NAO. But with traditional EOF analysis, the pattern doesn't change with time. So the pattern is static. So you will never find any change in the character of the NAO or any other mode of internal variability by this approach. So instead, you can turn your head 90 degrees and do what is termed snapshot EOF analysis. And snapshot is meant to convey that you're going to do the EOF at each point in time. That's the moment, the snapshot. And you're going to do it rather than EOF across time at a single time step. You're going to be sampling from these large ensembles all kinds of phases, random phases and amplitudes of these modes of variability, as I just explained at the beginning about large ensembles. And so that gives you a way, so you compute these EOFs at each time step, and you get what does ENSO look like at, as time moves along and as the forcing amplifies. So it really provides this direct way to assess whether there are any evolving force changes in these leading patterns of internal variability. So it's always a little hard to grasp it, but I think conceptually, it's pretty straightforward how we're leveraging these large ensembles. And remember, with EOF analysis, one removes the mean of the data before applying it. So in the traditional EOF, you've removed the time mean. So you're looking at anomalies with respect to the time mean. Here, you remove the ensemble mean, and the ensemble mean, if you have enough members, is the forced part, is the forced mean state part. So you've taken that out, so you know you're only looking at the internal variability about the force change in the mean state. Okay, so now I will come to my example, and I just show you, of course, just a few things, but hopefully show you that how insightful I think these two tools, when used together, can be. So in this paper, it was published in Journal of Climate in 2023 with J.P. O'Brien, postdoc, and myself. And we used the 40-member CESM1 large ensemble. And then we have a paper that's very close to being submitted, led by Nicola Maher and ourselves, and where she has repeated this technique with 8 different model large ensembles. So it's really building out our knowledge of this topic by examining other model large ensembles. Okay, so what we did, JP lived in California, or he did his PhD in California. So he really wanted to look at the North Pacific atmospheric circulation and how it impacts climate, especially rainfall in California. So we chose our study domain there over the North Pacific, and we did these snapshot EOFs on the 500 hectopascal geopotential height field. So it's an atmospheric circulation metric, and we went for the full period of the CSM1 from 1920 to 2100. And the interesting part, this region is particularly rich because it has intrinsic variability due to the jet stream and storm track, but it's also affected by teleconnections from ENSO in the tropical Pacific. So you'll see those two come together. Okay, so here is the leading snapshot EOF over the North Pacific in that red box. That's our study region in 1920. So that's across the 40 members. That's what that leading mode looks like. And then we regress the data everywhere onto the PC to get the global map. This is not the mean Pacific North American pattern. This is I put that little balance there. This is a mode of variability. So this could have the other sign. It could have, this is a 1 standard deviation amplitude. So this is just for convenience showing the positive phase of this mode. But it is variability. It's not just the mean. Okay. So that's what it looks like in 1920 in its positive phase, a strong Aleutian low, deep heights there, and then you can see some downstream centers of action. The model is very realistic when compared with the observations. So now I'm going to show you on the right an animation of this snapshot EUF that is done at each time step. It's not guaranteed that this mode will be the first mode as you go through time. You have to see, you have to discover if that is the case. And for this mode, it definitely is the case. So I'm going to keep 1920 on the left as the reference. And then in that green box in the upper right, that's going to be the year of the snapshot EUF that you will see. So here we go. So here we're in the 1930s, 1940s. Things are a little wobbly in terms of amplitude and pattern, coming and going. And now we're going to hit the 1990s. Now we're in the 2000s. So far, not a lot has happened to the mode compared to what it looked like in 1920. But now we are in the 2050s. And there you can really start to see some very systematic changes to the mode. And this will end at the end of the record there, 2098, like 2100 roughly. So you can still recognize that this is the PNA pattern, but its variability, that's what this is much stronger than it was in 1920, and it has a stronger linkage to the North Atlantic. So our present day or early 20th century PNA has definitely been modified by the radiative forcing. And then we can ask, how has that intensification of this pattern and also its expansion of its spatial footprint into the North Atlantic, how has that, what are the impacts of that? And we examined the precipitation impacts. So that's what I want to show you in this next figure. I'm not going to show you the animation. I'm just going to show you the two bookends of the time. So 1920 again on the left, 2100 on the right. And now the contours is what you saw as the shading before. That's the Z500 field. And again, it's variability. It's not the mean. And then the shading is the regression of the precipitation variability onto that mode. And you can see that as I said before, the circulation mode itself has intensified, but you can see the precipitation impacts right off the coast of California, and it includes California, are much more severe than they were back in 1920. So that's one notable change or impact. And then I mentioned this enhanced connection to the North Atlantic. So now all of a sudden, the NAO and the PNA are more connected than they have been, and that's very important. And then finally, you really see this strengthened linkage to the tropical Pacific in terms of precipitation. So then that led us to, this is just the last point I want to make, is, given that the linkage of the PNA in the future in this model to tropical Pacific rainfall is considerably stronger in the future, what is the influence of these tropical Pacific variability and teleconnections that will impact this Pacific North American pattern? So what we did was we can compute the snapshot EUFs of the tropical Pacific. We used SST. You could also use precipitation. And then we regressed out any linear dependence of the circulation field onto the tropical Pacific SST snapshot EUF. So we're just trying to linearly remove the influence of the tropical Pacific, assuming that the causality is from the tropics to the North Pacific, which is probably a reasonable but assumption, maybe not completely valid. But so that's what I'm showing you down here. These are the Z500 snapshot EOFs in 1920 and 2100 after we've removed that influence of the tropical Pacific. And you can see we've removed it because there's not much precipitation anomaly in the tropics. So our methodology has worked. And then what is very interesting is that you can see that, so this is what I call the intrinsic mid-latitude component of the PNA. PNA that projects onto the PNA. The PNA can arise just from, these teleconnections arise from just mid-latitude dynamics, but they can also be influenced by teleconnections from the tropics. So the intrinsic mid-latitude component has also intensified in the future, and you can see a little bit of intensified connection to the North Atlantic. It's not as pronounced as when you include the teleconnections from the tropical Pacific, but it definitely plays a role. So that's very interesting. And then the final point, just to summarize this paper that's in progress, is that for this mode of variability, there is strong agreement amongst the 8 model large ensembles that we examined that this PNA pattern will intensify in the future. This is variability, and it will expand its spatial footprint. And that's due to, we've done the same decomposition, and it's due to both changes in ENSO and changes in mid-latitude dynamics. So I will leave you with this just overall summary of what I think are interesting questions now that one can pursue, and that is how will anthropogenic forcing alter modes of climate variability? And I'd like to point to 2 resources if you're interested in using them. We've just released Adam Phillips, Nicola Maher, and so many people put in a huge amount of effort to assemble this second version of the multi-model large ensemble archive. And this is kind of a game changer, I think, for everybody who wants to use large ensembles. So there's now 18 model large ensembles. Each one has, between 30 and 100 members. It's just a huge archive. Also, we include observational data sets. Everything has been regridded to a common grid. So that painful step is already done for you, including the observations. So it's kind of one-stop shopping. And we include now 15 different atmospheric and oceanic variables, or quantities. So you can get the information there. And then I find for so much of my research, the ideas are sparked by using this climate variability diagnostics package that Adam Phillips really has pioneered for the community. So thank you very much.
Questions?
Yeah, thank you very much for a really nice, interesting talk. I was wondering about the snapshot EOF analysis. So how do you make sure that every model member and also at every time step you do capture the same leading mode? Like, do you need to filter the data before, or like?
No, and you're not guaranteed that it will. That's kind of the interesting thing. I mean, we thought, oh, maybe the PNA will start to, some other modes will become more important in the future. So that's interesting. So you don't want to presuppose anything. You're discovering what these modes are in the past and how they evolve in the future with forcing. The one thing that we did have to be careful about, so each time you do an EOF analysis, the sign of your EOF is arbitrary. So it was a little bit painful, but we had to, let's see, for each member at a given time step, I want to make sure it's the same sign. And so we just had to, ensure that, it has they have positive correlations rather than negative. But that was the only thing that you have to, that was the one thing that you had to pay attention to. But you keep the arbitrariness of the UF sign, just keep that consistent. But yeah, I think the beauty is you don't know, you know, if these modes, how they will evolve and whether there will be some mode switching. I tend to, you know, I don't think we should pay much attention to higher order modes for this paper. We actually did include the first 3 modes because the third one is particularly impactful for California rainfall. It's called the East Pacific pattern, and it intensifies as well. So maybe the higher order modes, there could be some mode switching, but we did not find that here. Yeah, I think she had her hand up.
Yeah, 2 questions. So based on the traditional UF analysis, when we do the historical UF analysis basically for the large ensembles, it tends to have like different mode 1, 2, 3 always have the different correlation with the spatial correlation of the mode is different with the observations. It can be matching very well with mode 2, but then sometimes mode 3 for different ensemble members. So like how does that showing on the snapshot UF analysis?
Yeah.
The second one is like how good the model performance would be for the tropical Pacific variabilities like teleconnections.
Yeah.
And it is like seasonal, like what you showed is winter time.
Yeah.
How about summertime? Yeah.
Right, yeah, yeah. Let me just, the first question. Sorry that it flew by. Just trigger me for the first question.
And traditional UF analysis
Oh
always
yeah, how
have,
do you compare with observations?
Yeah,
What you're saying, yeah. So we did that, but of course observations, you only have one sample at a given time step, so you cannot do snapshot UF. So when you want to assess the realism of these modes in the model, you have to use the traditional UF analysis. So what's interesting though is, so then you apply UF in the time domain as usual. And we did it for the period 1950 to whatever present, 2020 at the time. But what is interesting is that you apply the traditional UF analysis to each member of the large ensemble. They can be a little different. The amplitude can be different. The pattern can be a little different. You saw some of the wobbling of the animation. So then it makes you step back and your perspective on the observed mode is changed because the observed mode could be a little different if, we had longer record or some, alternate reality. So then to assess the model performance, you actually want to see whether the characteristics of, say, this PNA pattern in the observation sits within the spread of the EUFs across the members. So it's an interesting aspect. I'll defer the second question so we get other people.
I think I saw these hand first.
Yeah.
With the another question about the snapshot UF analysis, is there any way to look at asymmetries in the variability? Like maybe it's actually the positive mode that's increasing more than like the negative mode, or can you not really distinguish that in an EUF analysis?
Right, thanks for the question, it's a great question. Yeah, UF analysis is linear by construction, but actually our reviewers asked us that question. So what we did was you can, even though you're applying this linear analysis, so you get these PCs, snapshot PCs, they have loadings for each member at a given time step. And then you can just sort them and say, okay, let me composite the Z500 field for just the loadings, the members that have loadings above the 90th percentile, and those with loadings below the 10th percentile. So then you're looking at the two sides of the distribution separately. And we did find some nonlinearity, especially in this East Pacific pattern. I think it would be super interesting to apply nonlinear, pattern recognition techniques, if you will, to look at that more directly. I think it's important. Yeah, thanks.
Okay, because we have so many questions and we started a little bit late, let's push the schedule 5 minutes afterwards, okay?
Yeah, really interesting results. I'm wondering what the sort of leading theories for what the physical mechanism of how forcing leads to increased variability is.
Yes. So that is, I think, the important deep question to address, and we really haven't done that here. With regard to changes in ENSO, that is a very open area of research. Different models give different future projections of ENSO behavior. And it's not just the amplitude, it's also asymmetries, it's also how oscillatory ENSO is, its periodicity, all kinds of things. And ENSO is this delicate balance of lots of competing terms. So I think we don't have a really good theoretical foundation of how ENSO should change in the future. So that, to me, is a leading question that needs to be answered. And then this intrinsic mid-latitude dynamics, if you ignore or take ENSO out of the picture, there I think it's probably changes in the mean state, say the position of the jet stream, the strength, its shape, and then eddy mean flow interaction that can excite these modes. People have done work on the energetics of teleconnection patterns, but I haven't seen work on that energetic framework for how they will change in the future. Maybe on case read on that.
Take a question from back. Yeah, someone had an asked question. Yeah.
I'm wondering that to what extent do you think the leading UF mode is sensitive to the initial conditions in your large example analysis?
How sensitive the leading mode is to the initial condition?
Yes.
I don't think it's sensitive.
Okay.
So these initial condition perturbations, in the CESM, the perturbation amplitude in the temperatures 10 to the minus 14 degrees Kelvin. It's imperceptible. And yet now we get this huge spread. So what's happening is you're just, it's the usual kind of butterfly effect. You're just slightly altered, and then, you're walking down the street, and one day, there's a red light, and somebody runs it, and the next day at the same time, there isn't. That's the randomness. So there's some memory, of course, because the ocean initial state in the CSM, one large ensemble, was identical for each member. So we know there is some memory, generally less. If you're generous, you would say 10 years in some regions for SST, but really not for the atmosphere. So I think, everything we're talking about is not dependent on the memory of the initial state. I'm happy to continue, and I'm also happy to talk to people, you can find me.
Let's take one last quick question.
How long is the spin-up necessary for these simulations?
Actually, that's a great question. So a lot of work, of course, has to be done before large ensembles are launched. And those are the pre-industrial control runs. So first the model, as you're learning, has to be, each component has to be developed, and then they have to be coupled, and that gives you all kinds of issues. And then you finally get some kind of reasonable coupled model state that includes variability that is, reasonable enough. And then you run a long pre-industrial control run, so you do not change the rate of forcing at all. And then for the CSM1 large ensemble, we were tracking that, the pre-industrial control run. And It definitely has drift, and more drift the deeper in the ocean you go compared to the atmosphere. But then by about around year 300 or something, things looked like they were stabilizing. And so then we decided, okay, year 400, that's our random choice of our starting point for the large ensemble. So it's just because it was equilibrated at that point sufficiently. But it's a really good question, and now that large ensembles are just so widely conducted across modeling centers, we start to really have to scrutinize how were they initialized? Is there drift? Many models have tons of drift. CESM is actually, I think, one of the ones that has the least amount of it. So, and then also, do you perturb it with this tiny round-off error, or do you perturb the ocean initial condition? I recently wrote a paper on macro versus micro initialization for CESM2. If you're interested, that was published earlier this year.
Okay, let's thank Clara again. Between Clara's talk and our intro to lab. So Jesse, next we have Jesse. Jesse is a software engineer here at CGD, and he will talk about the intro to labs.
Great.
Clara still?
Can we use this mic? No, I can't.
Can we use that mic?
I'm still wearing it. Wait, is it yes? No.
Oh, okay. Okay.
Yeah.
Come on,
Hi, my name is Jesse Nussbaumer. I'm a software engineer at CGD in the section, so basically the folks who do CAM. The lab you're about to do in 10 minutes, which is the diagnostics one, which is where you actually plot the model results and do various analyses with it, kind of not what Claire just talked about, but kind of the tools to get to that point. So does this work? Yes. Yeah, so the goals, and maybe some of you already have this, like the community keeps shifting on me every year, but the goals are basically to learn about Python, particularly in a geoscience context, successfully run what are known as Jupyter notebooks in Jupyter Hub, which is our main tool we use here for kind of running Python and analyzing and running analysis. Visualize CESM model output, which I've heard people have had fun with already, and then learn kind of about the general different types of diagnostic software we're creating here at NCAR, both in CGD and also in CISL. And particularly, we'll emphasize, if you get the chance, will be Cupid, which will be the kind of main diagnostics package for CSM3, which is coming out at some point in the future. All right. So Python, if you're not aware, that's kind of right now the dominant software we're using for kind of any analysis after the model's been run. It's an interpreted multi-paradigm language, which is like fancy-smancy computer science speak, to say that it's essentially in a similar vein as things like MATLAB or NCL or IDL or Julia, if you use that. And we actually use it for a lot. In fact, all of the commands you've been running so far in the labs, create new case, case setup, case build, those are all Python scripts. If you were to actually just open them in a text editor, you'd see they're Python. But what we're talking about today is Python dedicated specifically to analyzing climate model data sets. And there's a whole wide community, and there's various kind of Python packages that we're using. Common ones include Xarray and NumPy, which is kind of what you'll use to read in netcdf data. Matplotlib and Cartopy, which are programs you use to plot data. And then other ones that I don't include here are things, we have SciPy libraries and Pandas and, like TensorFlow if you're doing AI machine learning stuff. But we're only going to do these ones for this lab. And so then in the lab, you're going to be using Jupyter Hub. And so what Jupyter Hub is actually a way through your web browser. You can essentially log into systems like Derecho, or in this case, it'll be Casper, which is our computer cluster used for scientific analysis, like not for running the model, but analyzing it afterwards. And Jupyter Hub allows you to log in and then run what are known as Jupyter notebooks, which you can actually create on the fly, but you can also take someone's already created notebook and run it, which we'll do today. So the login process is a little different than what you've been doing, so I'm just going to walk through it a little slowly. So you're going to go to the diagnostics part of the tutorial, and you're going to have to first, just through a terminal, log in to either Casper or Derecho. And the first step will be to do a git clone command, where you're actually going to clone all of these notebooks, or basically download all of these notebooks. After you've done that, you're going to go to that URL, which is also in the tutorial, and that's how you get to Jupyter Hub. So that giant red weight was because a few years ago, we tried this, and everyone logged in at once, and the system thought it was actually a denial of service attack, and so it shut down, and no one did anything for 3 hours. So, and not just us, like we took down the entire thing for all of NCAR, so it was cool. So we learned some lessons, and one of them is not have everyone do it all at once. And so instead what we'll try to do is when you all get seated, one of us will just come around and say, hey, this group, log in now. And then when they successfully log in, we'll move to another one. And that way we just don't hammer the system. That third bullet we can skip as long as we're doing it in groups. But another way to avoid this denial of service thing, which is explained in the tutorial notes, the lab notes, is in Duo, instead of just entering your password and waiting for it to ping you, you can actually open up, there's like a little show like numbers thing. There'll be 6 numbers. So if you type your password comma those numbers, you can get in instantly without having to wait for a ping. That is also useful if you're having internet problems because you don't have to wait for any ping back. Cool, moving on. Yep, awesome. All right, so real quick to talk about, so most of what you'll do in the lab, so we have a collection of notebooks for each component, right? So there's one that's analyzing like atmosphere, CAM output, one that's doing CLM, POP, et cetera. And so that kind of gives you exposure to how to plot the specific, netcdf files that are coming out of the model for that component, because some of them require regridding or specialized kind of analysis where you can plot it. But if you kind of can get through all that, or you're kind of like, I've done all this before, then we have some kind of advanced topics. So one of them is Cupid, which again is it's kind of this like full diagnostics package that we're right now targeting for CSM3. The idea being that essentially in the future, when you run a CSM simulation, this will automatically run after it and generate plots for you, whatever plots you want. So you don't actually have to do anything manually. Once the model's done, you'll have plots available. But this gives you a chance. You can also run it offline, so this gives you a chance to kind of experiment with it offline. The other big shift for CSM3 is almost everything will be on an unstructured grid, and unstructured grids are harder to plot because they're not nice flat lawns. So one of the things that CISL, our computing center, has been working on has been this UXarray, which you'll learn Xarray in this tutorial, which is helpful. And UXarray is essentially an extension of that, which allows you to work for unstructured grids. Yeah, and if you, like, for example, if you're in the atmosphere already, if you're working with the SE DICOR or MPAS, you would have to use the UXarray. CVDP, as Clara mentioned, right, this is a specialized package, particularly for looking at modes of variability. And we have kind of info here. I don't think we have a notebook where you actually run it because you kind of need longish model runs to really get info out. But have a lot of material. I definitely recommend checking it out. And there's work. Right now it's written in NCL, but there is work actively being done to move it to Python. And then finally, there's the ADF. The ADF is, and there's actually a LAN version of it now, so we should probably stop calling it the ADF, the LADDF. But essentially, it's another kind of one of these diagnostic packages where it allows you to run a bunch, basically generate a bunch of different analyses all at once and get a website out of it. And hopefully today, you can run the ADF directly, but if everything working out, Cupid will run ADF for you. And so, because the idea is eventually everything will go through Cupid. All right, that was it. So, any questions before we actually do stuff?
Yes! On your instruction slide, everything was numbered number 1.
Yeah, that was a test. I wanted to make sure people were paying attention. Yeah, you know, I will.
Just remember that if you're logging into Jupyter Hub, wait for we get to your table section before you push the login button. So that we don't kill Jupyter Hub your own target.
Yes, yeah.
Okay.
Unless you all want to go hiking or something instead. Yeah.
Okay.
You've been a good job. You've been doing a good job.
Oh, I appreciate that.
No,
Yeah.
that's great.
I started to realize how much work this is. Like, we're at time. Okay, welcome back, everyone. All right. Okay. This afternoon, the first lecture is from Gunter, and he will talk about land ice modeling in CESM. Okay. Come in. I'm going to close the door.
Hey, can you hear me okay? All right. Good afternoon. Nice to see you, everybody. I hope you're enjoying your week so far and you're learning a lot and not too overwhelmed. And I hope you're still going to be awake for my talk today, and which the goal is to give you a little bit of sense of the land ice work that we do here at NCAR with our community and our collaborators. And I'm not going to dive too deep into the details of the equation itself, but give you a wide overview of the science we do, how the model works, what it takes to do the model, and what we're going to do moving forwards. So I'm a project scientist here. I've been a project scientist for 8 years now, and I'm working in close collaboration with Bill Lipscomb, Kate Calder, who you met this week already, and Sama Minara, and or other collaborators within what is called the Land Ice Working Group. So as I mentioned, I'm going to talk briefly about land ice and sea level. As an introduction, I'm going to tell you a little bit about ice sheets and CSM, what we do, how we use it, and for what type of science we do, some research highlights that we've been working on, and recent and ongoing research. And let's start with land ice and sea level. First of all, let me define land ice so that we're all on the same level. What we call land ice is snow that falls and doesn't melt and eventually becomes ice under its own weight. And as it becomes ice, it begins to float under the force of gravity. Land ice is very different than sea ice because sea ice is frozen water, like you might have heard from Alice Duvivier earlier on this week. A little bit about sea level now. Sea level has been rising. It's not new. But what is new is that since about 1993, we've had satellite altimeters that were able to capture the actual change in sea level and give us more information about its global mean change. And since 1993, we can tell now that sea level has been rising by about 10 centimeters. There's 3 different sources of sea level. They come from thermal expansion, which is the volume of the ocean that grows as it grows or shrinks as it changes temperature. You have glaciers outside of Greenland and Antarctica, and then you have the 2 big ice sheets, Greenland and Antarctica. Before the 1990s, primarily the thermal expansion and the smaller glaciers were the bulk of the contributors for sea level, and Greenland and Antarctica were pretty much in mass balance, meaning whatever intake of ice they get, the same intake would go out of the ice sheets. Now, since 1990s, this is no longer true, and you can see by these numbers here that the Greenland ice sheet and both Antarctic ice sheets have started to contribute more and more to sea level, and now the combination of these two accounts for about 40% of the observed global mean sea level. We often talk about global mean sea level rise, which is an average around the globe, but really sea level is really a local effect. And again, thanks to satellite altimetry, here we can accurately capture the difference in sea level height around the globe. What you can see here in red is actually sea level, the higher sea level compared to other places, and in blue it's actually a sea level sink in some areas of the globe. So this is an average over about 25 years, and so in blue here this change is due to some ocean dynamics, complex ocean dynamics, and you can see different areas around the globe that are more subject to rise in sea level than others. The sea level rises, regional sea level rises, are due to effects like land subsidence, glacial rebounds, ocean circulation changes, but also due to the ice sheet self-gravity as well. What it means is that an ice sheet is a big block of mass, therefore it has a strong gravitational attraction. As it loses mass, this gravitational attraction lessens, and so it tends to pull mass away from it. So the ocean water that is strongly attracted to it, as it loses mass, tries to flow away from it. So it means in Antarctica, when Antarctica, can I point this? When Antarctica melts, that you can see in red, when Antarctica melts here, you can see, and it's losing mass, you actually have a sea level sink locally, and the water gets redistributed around the world. And the same happens in Greenland. So if you were to live, for example, in the continental US, you would hope more for Greenland losing mass as opposed to Antarctica. As I mentioned, so you have two continental ice sheets today, Greenland and Antarctica. And Greenland, which is in the northern hemisphere, has a reservoir of sea level that is about 7 meters of global mean sea level equivalent. It gains ice by snowfall, just like Antarctica, and it balances off surface runoff, surface melt due to warmer climate or warmer seasonal climate, and iceberg calving, which is when the ice breaks off from the ice sheet and becomes an iceberg. For a while, the Greenland ice sheet was in balance with itself until it started losing more and more mass and contributing more and more to sea level. Antarctica is slightly different in a way that, one, it's much bigger in size and has a potential contribution of about 60 meters of sea level equivalent. And just like Greenland, snowfall on Antarctica, but the way it loses mass is either by calving or basal melting from those big floating ice shelves. Big floating ice shelves that you have all around Antarctica. So here you have the Ronnie Feuchner ice shelves. Here you have the Ross ice shelf to give you a little bit of a sense of the size. They're as big as close to France. And so there's very little surface melt in Antarctica. Greenland has been losing mass at a pace of about 270 gigatons a year, which is about 3/4 of a millimeter of global mean sea level equivalent. And Antarctica is slightly less than that with 150 gigatons a year. So, of course, outside of these two ice sheets, you have smaller glaciers, also called mountain glaciers. And they're very small. All the glaciers combined in the world are very small compared to the two bigger ice sheets. If we were to melt all the smaller glaciers, sea level rise by about 40 centimeters, which is very small compared to the two big ice sheets. However, right now, the contribution to today's sea level is equivalent to the contribution of Greenland itself. One of the reasons for this is that they're very sensitive to warming in the area where they live in. So you have here an example of the Mer de Glace in France, which is a small glacier where it was in 1900 and where it is today. There's more like 100 meters of ice that was completely depleted. You also have like those bigger glaciers, also called ice caps, like the one you have in Iceland. They're also retreating a lot these years. Of course, besides sea level, when it comes to mountain glacier, you have other danger related to them. We rely on fresh water as human beings to live. And mountain glacier provide this fresh water to billions of people around the world. And as they lose their mass and keep shrinking, this water goes away. You also have other more catastrophic events, such that glacier collapse. You might have heard about the Berks Glacier in Switzerland, which collapsed in late May this year and just wiped out an entire village. Or you also have these what's called glacial lake outburst flood event. And this is an example that happened in Alaska near Juneau last year around the time. Now, a little bit about going into glaciers and how they move. Glaciers always have their maximum velocity at their surface and their minimum velocity at the bottom. They always flow downhill under the force of gravity. It forms just like a very viscous fluid. You can think about very thick honey. And the warmer a glacier gets, the faster it will flow. You have, in some part of the glaciers, you have the ice at the bottom who is frozen to the bed, and so the velocity flows very slowly. But eventually, you also have faster flowing ice, which sit on a bed that is very well lubricated with either meltwater from the ice itself, or sometimes from ocean water when it can penetrate under the bed. You also have saturated tills, so it's that can lead to fast-flowing glacier. When there is water at the bed, the glacier can slide at speed up to several kilometers a year, as opposed to tens of meters a year. In terms of dynamic and how we present them, we have different type of approximation that we use in the ice sheet model, and you might hear about this jargon. So we have, I keep messing it up. We have slowly deforming ice, which is frozen at the bed, that can be described with so-called shallow ice approximation, which works very well for the interior, in the interior of the ice sheets. But you also have another approximation called the shallow shelf approximation that works very well when you have very little vertical shear in the ice, and the ice flows very rapidly, which works pretty well typically in the outskirts of the ice sheets. You have more complex dynamics and capture both conditions here with the so-called Stokes equations. And one of the reasons why sometimes we might go with some approximation is because Stokes equations take a lot of computational resources to run. Now, I talked about ice sheets being in balance. And what we call balance is pretty much what comes in into the ice and what comes out. So this is called, that's how the ice sheet mass changes. And of course, when you have sea level change or sea level rise is when you lose more mass than you gain. Okay, so here, what you're looking at here, it's a coevolution of carbon dioxide, temperature anomaly, and sea level. So carbon dioxide, temperature anomaly, and sea level over the past 400,000 years. And what this figure shows is this cycle, 100,000-year cycle that happened in the climate to which CO2 and temperature anomaly kind of varied consistently together. But what we notice here, they did so quite well without any human involvement, but later on, there's this peak in carbon dioxide that is driving temperature up. These information came from Paleoclimate proxy data, and you're going to hear more about this with the next speaker this afternoon. And the reason why we care in the ice sheet community is because we can get some Paleoclimate record and also ice core record on telling us like what sea level was and a sense of what the ice sheet where the ice sheet was, where there wasn't any ice sheets. And you can see here, if you take this snapshot of 125,000 years ago, which corresponds to the last interglacial, there's a huge spike, huge increase in sea levels. This is when you had very big northern hemisphere ice sheet that covered North America that were formed. And throughout 100,000 years until the last about 20,000 years ago, you can see that sea level really dropped. So what we like about this is that we can take this information and try to study what happened then to try to predict the future. And if we look a little bit closely into the climate condition here, again with the last interglacial 125,000 years ago, the warming compared to today was about 1 or 2 degrees warmer, but the CO2 concentration was about 280 parts per million. So this warming of 1 or 2 degrees is very similar to what we experience today. So if we're able to represent with a model the condition of this time, it's a long time ago, but we might be able to gain some information of what the future looks like for the present ice sheets. And this figure that you see here is what we think the Greenland ice sheet looked like during this time. 3 million years ago, during the Pliocene, the warming compared to today, pre-industrial, was about 2 to 3 degrees warmer, and it had CO2 concentration that was very close to those that we have today. Interestingly, during that time, during this condition, sea level was 5 to 20 meters higher than it is today. So if this were to reproduce, because we're in similar condition today, this is what awaits us. Still need to be determined. We won't be here to experience it. But out of this 5 to 20 meters of sea level, up to 7 meters can come from Greenland, 5 meters can come from West Antarctica, which is here, and the rest would have to come from East Antarctica, which is the second half of Antarctica. It's unclear yet. We don't know yet for sure if the entire Greenland ice sheet melted at that time. But there's strong evidence that suggests that the West Antarctic ice sheets and some of the East Antarctic ice sheet had to collapse, for this to happen. And there's some paleo proxy record that somewhat validates this. In Antarctica here, there's a lot of instability, and I will show you in the next picture. It's because some of the bed of Antarctica lies below sea level. And so the interaction with the ocean for Antarctica is really important for this reason. Okay. So again, the reason for this instability is due to the ocean. And what you're looking at on the left-hand side here is the bed elevation in Antarctica. So in blue, everything that is in blue means that it's below sea level. Everything that is in green means that the bed topography lies above sea level. And all of West Antarctica here and a big part of East Antarctica lies below sea level. It means that the interaction with the ocean will matter, and the ice will react if the ocean water warms more and more. On the left-hand side here, you have a schematic of what is happening in Antarctica and how the ocean interacts with it. So in the Southern Ocean, you have these water masses, water layers that are warmer at depths compared to the surface water. And that's because they're saltier, and they're called circumpolar deep water. So the saltier, denser water can get warmer. And if they make it up the continental slope here and above the sea, they can enter the ice shelf cavity here and hit what is called the grounding line, which is a point of the ice where the grounded ice becomes to float. And by having warmer water attack this point of the ice sheet, it can cause retreat of the ice. Another impact here, and it's highlighted here, you can see here that the bed topography slopes downward as the ice moves forward. It's called a reverse sloping bed. And as you move backward here, the ice is thicker. In this condition, the ice is unstable. And as the ice goes thicker, as you move back downward, the ice flows faster. And this is what we call the marine ice sheet instability that you might have heard of. I want to be very clear about this. Sometimes this term is misused. It is what I consider a mathematical term. It's been, the mathematics explain it very well. Just because you have this condition doesn't mean you have marine ice sheet instability. There are many processes that can stop this instability. If you have buttressing on the side of the ice sheet, that can prevent this from happening. But nonetheless, as the ice widens and this buttressing becomes less and less, become more and more reduced, this phenomenon can happen, but it's not an automatism. I just want to be clear about this. So in terms of sea level projection, you might have heard about the IPCC report in our AR6, and where we're trying to estimate the sea level by the end of the century and how drastic it would be. And of course, these numbers are projections, they're based on models, and so they have a range of uncertainty associated with them. And right now, with the current path that we're under low emission scenario, we estimate that about 28 to 55 centimeters of sea level will happen by the end of the century. But if we don't work on cooling the climate and you keep moving forward, we could, and we end up in the high emission scenario, like the SSP 585 here, we can reach up to 1 meter of sea level contribution. But it's something to think about. Okay, ice sheets and CESM. So let's go a little bit into the modeling here. CESM is an Earth system model, and you're learning all about it this week. Prior to CCSM, it used to be called the CCSM, the Community Climate System Model, because at the time, it was only comprised of sea ice, ocean, atmosphere, and land. And eventually, we wanted to add more complexity, and so we added more components like biogeochemistry and the carbon cycle, and we thought, why not ice sheets? And so we included, the ice sheet model was included in CSM1, which started in 2010, which was the first complex Earth system model to include ice sheets. Earth system components don't like ice sheets very well. Ice sheets are troublemakers. And one of the reasons is that they have moving boundaries. And CSM at the time didn't like this because we had the pop ocean model, fixed boundaries, the land model, fixed boundaries. And so now when you add, when you add an ice sheet model that said, no, I'm growing and I'm shrinking, well, you're breaking all of these conditions. So it took a lot of work to put into it. So originally, we did the work. You got into it, obviously, it's there. But we had to do this using simplifying assumption. Like I mentioned before, the shallow ice dynamics. So it's not very accurate for ice stream and ice shelves, but it was very accurate for the ice that's within the interior of the ice sheet. And it was done in a one-way coupling way. So this means that the ice sheet could experience a change in the climate, but in reverse, the climate will not experience a change in the ice sheet at all. I talked about mass balance before. In order to grow an ice sheet, you need some ice to accumulate on it. And the ice sheet model doesn't do that, doesn't do anything about accumulation, things like this. It relies on the climate community land model to pass this information. So we have the land model that takes this information from the atmosphere on a very coarse resolution that is about 50 to 100 kilometers, passes this information to a coupler, and then each grid of the land model has what is called elevation classes, so that it can melt and grow, melt or accumulate snow at different elevation within a grid cell, so that when we then downscale this information onto the CESM grid, which is more like 4 kilometers typically, we do not lose information based on the ice sheet topography. Once this information is passed, then the ice sheet model computes the ice flow of the ice and can evolve dynamically. Now, in CSM2, which is the older version, the newer version of the model which you're using right now during your tutorial, we relax those simplifying assumptions about shallow ice dynamics and one-way coupling. Now, CSM2 supports a fully interactive coupling between the grid and ice sheet and the system, meaning that when the ice sheet evolves dynamically, the climate can respond to it and see these changes. So the way it works is that CLM passes a mass balance to the ice sheet, and in return, the ice sheet sends back a change in elevation and a change in surface area. As CLM is also, has different land types, dynamical land types, and land units for its grid cell, this can evolve dynamically as well. And so wherever the ice sheet sits, those cells are glaciated cells, the glacial cells, and once those cells are free of ice, they can become vegetated again, and this has an impact on albedo and other processes. So if we put this into a schematic, and you might have seen such a schematic already, so you have the ice sheet model that deals with the ice sheet dynamics that communicates with the land through the coupler, and eventually, once in a while, it also tells the atmosphere how it has changed its elevation. And something I haven't talked about much is what happens into the ocean with the ice sheet. So when the ice melts or calves, well, we have to do something with this ice. We cannot just leave it there. And well, the ocean takes it. When the for surface melt, we just send a surface freshwater fluxes to the ocean. But when the ice calves, we have to send this block of ice into the ocean. We don't have an iceberg model, so we cannot have this iceberg drift and slowly melt wherever they're drifting with the ocean currents. So what we do instead is that we take heat from the ocean, the necessary heat that melts the ice, and then we redistribute this ice over a certain region. So in order to evolve your ice sheet dynamically in the model, you need to initialize it. And this takes a lot of work and has some assumptions in it. In order to do this, you need some information. Some of this information is a bed topography, where the layer of the land of where the ice is going to sit, and the ice surface elevation. And from these two, you can compute an ice thickness. What you also need is a surface temperature and a surface mass balance, which we get typically from regional climate model or a system model. You also need what is called a geothermal heat flux as a boundary for the ice at the bed. It's a thermal boundary. And especially when you deal with ice sheets like Antarctica, you need a ocean thermal forcing, so you have some information to pass to the bottom of the ice under ice shelves. With all of this information, what happens, we tune the model to match thickness observation the best, and we do this by adjusting the basal friction coefficient. The basal friction is a resistance of the ice, that is of the ice at the bed, that we know very little of. So whatever needs to be shoved under the rug to make the model look like, that's, a lot of it goes there. A spin up for the ice sheet takes about 10,000 years. We get this in a day or two. And then once we have a good when we have a good equilibrium here, we can then pass this information onto the system model. And typically, what we do, the spin up of the ice sheet model is done offline with the ice sheet model as a standalone model. We don't do this in a fully coupled way within the CESM framework. This would take too long, and that would be unnecessary. But when it comes to CESM, and when we want to evolve your ice sheet fully coupled, after we've done this offline initialization, you do feed it back and evolve it fully coupled to have the climate adjust to the new shape of the ice sheet that had to relax based on the inversion process. Even though we try to nudge for ice sheet thickness, the beauty of the process here, at least for us, is that whenever you match the thickness well, it turns out that you match the velocity compared to observation very well as well. And this is an example. On the left-hand side here, you have the observed surface ice speed on the log scale, and you have a resulting spin up of the entire ice sheet here after 20,000 years. And you can see that they agree pretty well with some discrepancy there and there. But overall, it looks pretty good. When we do ice sheet initialization, typically we do them to reach a steady state, meaning the ice will be fully equilibrium with the climate. And unfortunately, a lot of the ice sheets are not in steady state. There's an imbalance, and there's an imbalance in the process that is typically not captured in this. To try to remedy this problem, we implemented a new methodology that takes into account the observed rate of ice thickness change that you can see as an example here on the left-hand side. Whatever is in red is a stronger thickness change loss, and in blue is when you have a thickness change that is growing. And you can see in the Western Antarctic, you have a lot of change, in particular in the Thwaites and Panamanian glaciers are. But you also have some accumulation due to snow on the Ross Ice Shelf in the Queen Maud Land here. So what we do, we take this information into the spin-up process, and we initialize with this change included in the process, such that at the end of the spin-up, when we run the model forward, we actually can capture this change in from the get-go, which is different from a fully equilibrium spun-up model. So we've done this. It works pretty well. And when we do this, meaning like including this into the spin-up, meaning that these are the current condition of change of the ice sheet, meaning, and when we run forward with this condition without any additional climate change or surface or ocean warming, we expect that within 1,000 years, the entire a lot of the West Antarctic ice sheet has collapses under current condition. Typically, we get, at least for CSM, we need a good surface mass balance representation, and we would take this from CSM. In order to do this, to compare our product, we use WACCM, which is a regional Arctic model, and that is tuned to match observation. And in CSM2, it's run at a higher resolution, about 10 to 20 kilometer, compared to CSM, which has a resolution that's 5 times coarser. But overall, in CSM2, you can see that here in blue, you have positive surface mass balance, and in red along the coast here, you have negative surface mass balance, also called the ablation zone. But overall, when you look at the patterns, they match pretty well in CSM2 compared to WACCM, which gives us some confidence that the climate is in the right state, and we can use this information to sensibly evolve Greenland ice sheet in present day and have sensible results. However, even though the pattern look pretty good, we still have an excess bias of accumulation in the south here that we're trying to work on improving. We're working into producing CSM3 right now, and the surface mass balance right now so far looks very similar to what we have in CSM2. Okay, a few research highlights. How am I doing? Oh, okay. So, okay. We participated in the ice sheet model intercomparison project, ISMEP6. This was done for standalone, in a standalone ice sheet way. And to go faster around this, for Greenland, all the model agreed pretty well with one another, where until the end of the century, Greenland is going to experience a lot of melt. And all the models that participate in this effort had consistent behavior with respect to this. However, in Antarctica, which is fairly new, relatively speaking, the numbers are all over the place. And you can see for the West Antarctic ice sheet, you have strong contribution, lower contribution, but it's all over the place. So there's a lot of uncertainty in the projection from the Antarctic ice sheet. When it comes to the fully coupled simulation with an evolving Greenland ice sheet, we did such an experiment with CSM2 evolving until 2100 under warming scenario. And you can see, sorry, here the color scale is reversed compared to the previous plot where the ablation zone is in blue. And you can see advancing in time under warming scenario, the ablation zone keeps increasing, increasing, and increasing more and more. So that there's a lot of contribution from the Greenland ice sheet to sea level in this experiment, up to 10 centimeters by the end of the century. We also use the CSM to do paleoclimate simulation fully coupled, and we did this 4 years ago, where we simulated the last interglacial 127,000 years ago for 8,000 years. And in this simulation, what we did, we updated the vegetation every 500 years using the biome vegetation model because vegetation model within CSM was not as mature. And what this led to is, you can see throughout the simulation, which changed with orbital configuration, that the Greenland ice sheet slowly retreated to reach a minimum at about 121,000 years ago to eventually slowly grow again. And the impact of the vegetation versus not having it was huge. a factor of 2 of sea level contribution. And this is because of the albedo feedback of the vegetation on the system. Let me skip through this. And so for future work and study, what we're trying to do for the new release of CESM, the ice sheet model itself, is to improve on the subglacial hydrology based on sliding and iceberg calving. We improve also on the initialization method, like I just talked about, and we also want to use CESM to simulate mountain glacier. As far as CSM3 goes, we want to minimize the bias of Greenland mass balance, but also support fully coupled climate ice sheet simulation with Antarctic and Paleo ice sheets. Let me skip about hydrology. Pretty much what this slide says is that we have a scheme that is implemented right now that does a very good job of representing the basal hydrology in the ice sheet at a very modest cost. In terms of calving, we are participating in the calving intercomparison project where we can compare our model to others and pretty much reassure that our dynamics and numerics work properly. On the more realistic side with Antarctica, we started implementing some calving schemes that are based on thickness and stresses that lead to pretty much to very good agreement with observation of the calving, but this is still an ongoing effort. In terms of mountain glacier, we used CESM. Now we have put the logic in CESM to actually model mountain glacier, and we do this at a way higher resolution of about 100 meters compared to the ice sheet. And what you see here is an example of the simulation of the entire Alps. On top here you have the Mont Blanc and the French Alps, or here the Bernese Alps and the Alleged Glacier. And we did an experiment to see what would happen to this glacier if they were not subject to any more warming than what you have today. And pretty much in the Alps, those glaciers would lose, in average, 63% of their mass and their volume. In terms of fully covered ice sheet for Antarctica, with MOM6 now, which allow cavity ocean circulation, we can have the ocean reach the ice sheet cavity, the ice shelf cavities, and have this interaction with Antarctica to better represent the Antarctic evolution within CSM. But even though this is capable, this is not yet validated. We have the full capability of doing this, and we're still working actively on this. Last slide. Here, this is a future development that we're working on. So of course, we did the Alps with the glaciers. We want to do other regions like Hammerland Asia or Patagonia and so on. If anybody of you is interested in this, let me know and we can work on this together. We're also interested in adding solid earth as a new component within CSM so that we can capture the sea level variation around the globe, but also the rebound of the earth under the ice when the ice load changes. Quick summary of what I've told already. And here, if you want to know more about land ice work that we do here, feel free to contact us. So I'm here. There's my contact information here. I'm the coach of the land ice working group, but also the science liaison for land ice science here. Kate Calder is also a good person to contact. She's a software liaison of this group. And Bill Lipscomb, who's the lead CESM developer. Thank you.
For Governor.
For the mountain glaciers, when you do the estimation of or the parameterization of the bed topography and using the shallow ice approximation, how does the impact differences between ice sheet? Because ice sheet can be wide open, right, ice cap, but then for the mountain you have to have the boundaries for the basins.
We have those boundaries, so we do have, there is data about those bed topography for glaciers as well. And we do not use a shallow ice approximation for the glaciers we use. Well, it's an approximation called the depth integrated vertical approximation, which is the same dynamic scheme that we use for ice sheets. So this stays the same. As far as the basal friction goes right now, we have a scheme for which we set a coefficient, and when we spin up the glaciers, what we use, we have coefficient to spin up with respect to tune the climate, because this is the biggest unknown in the glaciers. There's very little data on the lapse rate, for example, that we don't know within the glacier system. So there's not a profile that we know. So in terms of containing those ice within the bed, we have this information, and we can do that.
Hi, thanks for your talk. I have a question regarding the iceberg. Like when it breaks from the ice sheet, you said that you would let the ocean heat this iceberg, and then don't you introduce like too much freshwater flux into the ocean? I'm just thinking about the ocean circulation, for example, AMOC, you know, and there are a lot of, I think, some papers also talking about, yeah.
No, that is definitely a concern. So because we don't have a good distribution of icebergs and where they drift and so on. You have other models that actually do this. But the way we do it, we take the energy, we don't do this over a single grid cell of the ocean. So like, as I mentioned, we spread this effort, and I think it's within a 300-kilometer radius, if I remember correctly. So it's not just local, we spread this. And so this minimizes the effect that you're mentioning here. Otherwise, you're right, it could have some unwanted effects.
Okay, and that's like negligible.
I mean, that's what we do so far, and so far so good.
Similar to the same kind of follow-up on that question, you mentioned that in CSM 1, there's a one-way coupling between the ice sheet and the ocean, and then subsequently you guys changed that. I'm still very unclear on how this, and I guess it might be similar to sea ice as well, that you have this expanding and contraction of the amount of the ice that's available to interact with the ocean. So how is that actually getting kind of coded in CSM? How is that coupling happening?
So are you worried about the one-way coupling as opposed to the two-way coupling?
Yeah.
So in a one-way coupling, the ice sheet does not dynamically evolve. So it remains pretty much static, right? There's no dynamic. So in terms of boundary changing, this stays fixed, right? Which is different in two-way coupling. And so what was the confusion here?
I guess I'm just like unclear on how that coupling works when your boundary keeps changing in the two-way coupling.
So when the boundaries are changing, the information, so when the boundary, let's assume the Greenland actually is shrinking. So you have a reduced surface area and volume, right? And so this changes, the land ice is going to exchange a freshwater flux with the system. So you have liquid and solid freshwater fluxes. There's a solid for the icebergs and the liquid from the ice that has melted on top of the Greenland ice sheet. This will be sent to the ocean, and the ocean will take this into account into this circulation and dynamics and everything. But that's how it works. And then for the change of the area, this is when you don't have any ice shelves. So the land is going to take this into account. So if your question is about how is the ocean going to see this change, okay, very good question. So in POP, in CSM1, POP didn't care because it was a fixed boundary ocean. So it initialized at the present day where the ice sheet was, and wherever the calving front was, the POP would say, this is where my boundary with the ice sheet is. And then when the ice sheet would retreat, it wouldn't know that it had retreated. It would keep adding those freshwater fluxes because you could compensate this with changing the density, water densities, for example. And so now with MOM6 right now can still have those fixed boundaries, but it can also move those boundaries. And we're going to work towards this later option. Does that make sense?
Yeah, I mean, I'm still just trying to understand how it works.
No, it's complicated, yeah.
For your example on the last interglacial ice sheet, I'm curious whether we have geological evidence to support or compare with your climate model simulations, whether it's giving us this reasonable shrink of ice sheet or something.
That is a very good question. There's some evidence. Let's see if it's on the plot. Okay. So here, what you can see on this picture here, C and S and R, there and D, those are all ice coring sites. You know, and so when you drill through the cores, you can tell whether there was ice there at some period of time, depending on the ice age, for example. And you know, it's sparse. There's very little, but that's what we have. And so if we could at least, you know, have some good agreement between our simulation and the state of those core sites, then that's a good indication that what we do is not completely absurd. That is definitely definitely something that provides a limitation on the simulation exercises. So I'm looking for volunteer to, you know, to add to this map.
Okay, if there's no more questions, let's thank Gunter again. Okay, everyone. Now,
Is that good? Test, test.
Wait, am I turned on?
okay.
Am I okay? Can people hear me? Is that? Oh, they, okay, thank you.
So let's now hear from Sophia talking about paleoclimate.
I'll try to be fast. Okay, hi, I'm Sophia Makarowicz. I'm a project scientist in the Paleo and Polar Climate section, and my specialty is paleoclimate applications with CESM. So that's what I'll be talking about today. I'm gonna get right into the first slide. So why do we study paleoclimate with CESM? Well, to showcase this, I'll show you the past 100 million years of global mean temperature and CO2. And what we can see from this plot is that for most of the past 100 million years, the CO2 was much higher and the Earth was much warmer than it is today. And this is actually a really good thing because over our very short observational record, we do not have measurements of a higher CO2 state. And so paleoclimate is really the only option we have to have real data to validate climate dynamics under a high CO2 scenario. And so that's really what we try to do in the paleoclimate group. And the high CO2 state I'll be talking about mostly today is the early Eocene, about 50 million years ago, and that's been related to sort of a high emissions SSP5 8.5 scenario. So on the left is the world during the Eocene. It was very hot. This is the early Eocene climatic optimum. About 50 million years ago, high CO2 around 1,000 ppm or higher. There were no permanent land ice sheets during this time. It's a hothouse. Then on the right, we have the other extreme, which is the last glacial maximum about 21,000 years ago, which had low CO2 around 180 ppm. And this is also a really interesting time period to study. You see these really expansive ice sheets across the northern hemisphere, so we can ask questions about ice sheet stability, sea level change, and because it's much more recent, we have many more proxy records to compare our simulations with. So I hope to convince you in this talk that it's really important to test CESM under extreme climate states, both warm and cold. So during the early Eocene, there is fossil evidence for the coryphodon or hippo-like animal in the high Arctic along with a deciduous forest ecosystem. And on the other end of things, during the last glacial maximum, there's widespread fossil evidence for these woolly mammoths that were thought to be the most widespread distribution of any large mammal. They are related to modern-day elephants, but they have these special adaptations with long hair and small ears to adapt to the extreme cold. So this is our sort of first line of evidence to indicate that these were very warm and cold climate states, but this is quite qualitative. And so what we like to do in paleoclimate is find quantitative estimates of past climate processes and fields using proxy data. So proxy data can be a lot of different things. Proxies are our real world climate data beyond the record of direct measurements. So proxies can be physical, like a human taking a record of a storm passing over a ship. They could be chemical, like a coral calcium carbonate skeleton that's recording the surrounding chemistry and temperature of the seawater around it. They can be biological, like a tree ring. We can look at the width of those rings to reconstruct something like temperature or precipitation in the past. And so all sorts of proxy records can be used to reconstruct a number of processes. This is just sort of a subset of the different processes that we can start to constrain using proxy information. And this is really the foundation of our data that we use to validate paleoclimate simulations. One specific example I want to dive into in this talk is using proxies to reconstruct temperature in the past. So benthic foraminifera are these single-cell organisms in the ocean that are really some of our best sources of reconstructing temperature in the past. They incorporate ions from the seawater into their shells, and that happens as a function of temperature. And so we can convert the chemistry of their shell into past seawater temperature. And so this is a high resolution record of temperature across the past 65 million years. And I show you this so that I can now sort of move on to how we leverage that information to validate CESM. So now let's get into some simulations. On the left is the early Eocene. On the right is the last glacial maximum, and in the gray shaded areas, that's our proxy estimate for temperature during each of these time periods. And so our goal from the CESM perspective is to run a simulation of each of these time periods that falls within that range of global mean surface temperature for each of these time periods, and ideally do that with the same version of CESM. So it can simulate both extreme climate states. But if we look at the red lines, that's the default version of CESM2. You'll see that during the early Eocene, the temperatures are much too high, and during the last glacial maximum, the temperatures are far too low. So there's something going on in this model that can't capture these climate states. On the other hand, if we look at CESM2 with CAM5, so that's CAM and CESM1, in the brown lines, you'll see it falls within those reasonable temperature ranges. So something happened between CAM5 and CAM6 to produce these unreasonable temperature estimates, but there's a lot of differences in the parameterizations between CAM5 and CAM6. So this work was led by Jung Zhu, who's another paleoclimate scientist in CGD, and he went on a journey to figure out which parameterization is causing the issue. And at the end of it, he ended up making adjustments to the moist turbulence scheme, the cloud microphysics scheme, and the ice nucleation scheme in CAM6 in order to get a paleo-calibrated version of CESM2 that can reasonably simulate temperatures for both the Eocene and the last glacial maximum. So that's in the cyan line. Breathe. Oh. Okay. But so that's exciting, because now we have a version of CESM2 that we can use to get reasonable temperatures for not only this hot house, the ice house, but also historical time period. And so what I also want to highlight in all of these dashed lines at the bottom is that that's the same experiments done with one-time CO2, so pre-industrial conditions, and you can see that all these changes we made had very little impact on the modern day or near modern climate state. So that underscores the importance of testing the parameterizations under a wide range of climate states. Okay, now I want to go into like 3 aspects of CESM that are really important for paleoclimate applications. And the first one is water isotope tracers. So when I talk about water isotopes, I'm talking about different molecules of water can have slightly differing weights. And so on the right here, you can see that this is like a water molecule, nice, that has an oxygen with 16 protons, and that's lighter than a water molecule with an oxygen that has 18 protons. And so the sort of meaning of this is that when there are phase changes in water, these versions of water will partition differently throughout the water cycle. And so we can learn about water cycle processes and also temperature from looking at the relative composition of heavy to light water. And so when you think about a proxy system, like a foram, when it's swimming along or floating along in the water column, it is recording the isotopes in the water column and incorporating it into its shell. And so we can reconstruct both, as I said, temperature, but also the isotopic composition of the surrounding seawater. And so that means that the unit that's kind of recorded in the foram is very different than what we typically get from a climate model. So there's sort of a language barrier between what the climate model outputs and what the actual proxy is recording. And so when we incorporate water isotope tracers in CESM, we can actually start to do these sort of apple-to-apple comparisons between the simulation and the proxy. So now I'll go over sort of an example of how these water isotope tracers really improve our proxy model comparisons. And I'll use the term delta 18O, which is just the ratio of heavy to light oxygen. And it's just the unit we use. And so I'll pose this question because I know all of you have lied awake at night and you can't fall asleep and you're thinking, how much colder was the ocean during the last glacial maximum than it is today? I really have to know. Okay, we're gonna get the answer right now. So we're gonna look at our forams because they're starting to record the seawater temperature in the past. But as I said, there's 2 different things I said that can influence foram delta 18O. It's both the seawater temperature, but also the seawater delta 18O. And so you might think to yourself, okay, I've got to come up with an estimate of seawater delta 18O. And so I know there is a really important impact of global ice volume on seawater delta 18O. During the last glacial maximum, we had these really expansive ice sheets. They're locking up a ton of light water. That means the ocean is relatively high in delta 18O. So we can come up with a simple global approximation of seawater delta 18O based on ice volume. But we also know that seawater delta 18O varies with a lot of other things, like ocean circulation and the balance of precipitation to evaporation. And so there's a lot of regional variability in this actual value. So that's where our isotope-enabled CESM comes in, and we actually can estimate seawater delta 18O in every location where we have a foram. And so then we can calculate our seawater temperature based on the forams with that information. Combine that with the independent estimate of seawater temperature from CESM, and now we get a really robust estimate of seawater temperature in the past, and it was about 5 to 6 degrees cooler. Now you can go to sleep. Not now, though. And so the second aspect of paleoclimate simulations that's really important is having a cheap version of CESM. So that's CESM with a low horizontal grid resolution, about 100 kilometers or greater. And the reason this is so important is because there's a lot of uncertainty when it comes to understanding the boundary conditions and forcings in past climate simulations. Like, for instance, during the Eocene, we know CO2 was a lot higher, but the actual amount of CO2 is fairly uncertain. And so what we can do is run several climate simulations with varying plausible CO2 to capture that range of uncertainty. So here's global mean surface temperature and then mean ocean temperature on the bottom in 4 different CO2 scenarios. And you can see that it also takes a while for those simulations to reach quasi-equilibrium and have that kind of flat trend. So we also have to run these simulations for sometimes over 2,000 years to reach that quasi-equilibrium state. So both of those aspects mean it's really important to have a low-res version of CESM. But we also want to leverage higher grid resolution for paleoclimate applications because we know there's a ton of benefits from higher grid resolution. So for instance, one thing we know is that tropical cyclones are better resolved with higher grid resolution. So here's the spaghetti plots of historical tropical cyclone tracks, and then we have a high-res CESM simulation and a low-res CESM simulation, and you can see that the spaghetti plots compare a lot better with the observations in high-res CESM. And so luckily, we have a configuration of this high-res CESM, which has a 25-kilometer atmosphere and land and a 10-kilometer ocean and sea ice component with water isotope tracers. And so that means we can start to leverage this for extreme precipitation in the past. And one other exciting aspect of this high-res configuration is it relies less on parameterizations. So at the 100-kilometer scale, you have a parameterization for mesoscale ocean eddy mixing, and at 10-kilometer scale, you explicitly resolve these features. And so we have taken this high-res configuration of CESM and run several simulations, including our hothouse Eocene and the last glacial maximum. And we've been able to find a few interesting things about tropical cyclones over the North Atlantic. The first is that the last glacial maximum has fewer tropical cyclones, which makes sense. But also, there are a lot of interesting parallels between the Eocene simulation and an RCP 8.5 scenario. The first is tropical cyclones extend farther north or farther poleward. The deep tropics become more hostile for tropical cyclone development, and there are more Cat 3 and stronger hurricanes. And so while we can't validate RCP 8.5 from an observational perspective, we can start to think about validating the paleoclimate simulations with this respect. How would we do that with proxy data? So there's a field called paleotempestology. And so let's say you have a tropical cyclone that's moving over the eastern US, and you could imagine that in some example of a coastal ecosystem on the right here, that you have the the water coming up to the coast, you have the sand berm, and then you have sand behind it. And under normal circumstances, marine sediments are not going to get washed over this berm. But when the tropical cyclone comes, you have an extreme storm surge, and that kicks up a bunch of marine sediment and pushes it farther inland where it couldn't be otherwise unless there was really strong storm and waviness. And then after the storm passes over, the coast settles back down, and then the normal sand is deposited again. So you could take a sediment column farther inland and see these intermittent layers of marine sediments and reconstruct a time series of tropical cyclone frequency and intensity. So that's what we're starting to think about a lot in the paleoclimate group. Am I over time? Oh, I have 8 minutes? Oh, total. Oh, perfect. Okay. Now, okay. The kind of final section of this talk is that I want to give you I'll slow down then. I want to give you, how many? Okay, that makes more sense. Okay. So now I want to give you an idea of how you would design your own paleoclimate simulation. What are all the major steps that you might take to generate your own run? And so at the beginning of this week, all of you started by generating your own so-called out-of-the-box default pre-industrial CESM case. How would we get from that all the way down to a paleoclimate CESM case? And this is kind of an extreme scenario, but this is like the supercontinent Pangea. And the reason I'm going all the way 300 million years back is because I studied this during my PhD, and I think it's cool, but also because it's going to show you every possible step you would have to take in this sort of workflow. But just note that if you're interested in more recent time intervals, you won't have to do all of these steps. So the first is thinking about, has continental drift played a role in the paleo time period you are interested in, and you have to adjust the land sea mask. You have to input a new continental configuration, tell the model what the topography was on those continents, where the sea level was, and what the bathymetry is. On those new continents, you have to make a new land surface data set. So in this land surface data set, you have to tell the model where should the new vegetation go? Where are the tropical forests? Where are the deserts? Are there large lakes on the land surface? Were there ice sheets during this time? What is the new river network that runs over these continents? Next, there's likely some different external forcing during this time period. So the Earth might have been in a different orbital configuration. The solar luminosity may even have been different. 300 million years ago, it's thought that the solar luminosity was about 2.5% lower. You'll have to think about the atmospheric composition. Were the greenhouse gas concentrations different during this time you're interested in? How should you treat the aerosols? And then once you've created all of those different input files to put into CESM, you'll want to run a test case to see, are any of the parameterizations behaving a little funny? As we saw in Jung's work, where he investigated all these different cloud parameterizations, there were some issues when you tried to run CESM in this extreme hothouse scenario and an extreme cold scenario. And so that can be a lengthy process. Oh, can I answer it after? Okay. That can be a lengthy process, but the exciting part of this is that when you find a fix to a parameterization that can work under a wide range of climate states, you're feeding back onto CESM development. And then finally, in your production case, you'll have to think about how to initialize that simulation. So you have this new ocean where you have to give it a new temperature and salinity profile, and the way you set that is going to impact how long it takes that simulation to spin up. So no one is an expert in all these different steps. It's a very collaborative, interdisciplinary process, and so it's really valuable to have collaborators, particularly at universities such as paleobotanists, chemists, and other geologists to help you with each of these steps. And then after probably some debugging, you will have a deep time paleo simulation, and in the paleo group, we will applaud you for this. It's a great accomplishment. And so I'll just leave you with a few things. Paleo is used in the development and assessment of CESM. Isotope capability in CESM 1.3 is critical for proxy model integration. Paleo requires low-res, long simulations to assess uncertainty. and leverages high-res for studying past weather extremes. Paleo relies on interdisciplinary expertise of colleagues at universities to help design boundary conditions and forcings for CESM. And I guess I'll just leave this up, but the one thing I want to say is if you're interested in developing a paleoclimate simulation, don't be intimidated by all those steps that I outlined, because we already have a really strong set of existing simulations, and we always say start from something that's been done before starting from scratch. And if you're interested in the simulations that are available, you can scan the QR code.
Is there any plans to move, I think you're using the version CSM 1.3 to have the same version that all the other teams are using? Why is a different version? Like so?
Oh yeah, I forgot to say this. Thank you. So with respect to the isotopes, they're only currently implemented in CESM 1. And so we have a grant right now to implement the isotopes in CESM 3, but they're not currently in there. And the isotopes tend to be this critical thing to compare with the proxy data, which is our strength, is having that proxy data. So we tend to use CESM 1. And in the high-res configuration I talked about, we don't have a high-res configuration of CESM 2 or 3. It's far more expensive, so they use CESM 1.
So for your paleo hurricane examples during the Eocene versus the RCP 8.5, I noticed that we don't have a lot of like hurricane initiated in the tropics. Why would that be?
Question. I'll go back to the slide, but to be honest with you, oh no, I have so many. To be honest with you, this is Betty Otto Bluesner, her study. And so she's writing a paper right now on like the environmental conditions that cause you to have more hostile environment in the deep tropics. And so I can't speak to it. Yeah, right there.
Regarding the high-res run, I know there was a lot of work done for the pre-industrial spin-up. How did y'all initialize this Eocene and LGM?
Great question. So for every single high-res run we did, we had to spin up a low-res configuration. So we'll spin up, like with all the same boundary conditions, spin up a 1-degree ocean and a 1-degree atmosphere run, and then we will branch the high-res off of the low-res run.
Oh.
Yeah. So these runs are only, around 50 years.
Okay.
Yeah. And then the low-res would be 1,500 years or 2,000 years long.
Did y'all do any ensemble spreads for those, or just one realization?
For the low-res?
For the high-res realizations of this.
Oh, for the high-res? No, we haven't done any ensembles for the high-res. They are quite expensive, especially with the isotope tracers added in. But for a couple of our time periods, we're doing vegetation sensitivities. Like for example, for the Holocene, we're running a couple different vegetation scenarios. But that's like, we're slowly developing more.
You mentioned that the parameters that would be used to replicate the Eocene and the LGM were attempted to be the same while you're reconstructing them. Why would that be the case, assuming that they're essentially two different worlds? Why would we want to?
Can you repeat the question one more time?
The parameters that were tuned for creating the Eocene and the LGM simulations, they were attempted to be the same. Is that what you mentioned?
Yeah.
And I'm just curious, why would that be the case, assuming there's such different climate worlds, essentially?
Yeah. So.
It's almost like two different Earths.
Yes, and they very much are. So what's interesting is that Jung ended up modifying 3 different parameterizations, but it turned out that the moist turbulence scheme was really the important parameterization change for the Eocene, and then the ice nucleation and the cloud microphysics was really important for the LGM, highlighting that there's sort of different processes that are important for both of those very different climate states. But at the same time, we don't want to tune one specific version of the model for one specific climate state. We want ideally a similar version that can work over a large range. And so he modified all three parameterizations so it could function well for both the Eocene, LGM, and historical.
Thank you for the talk. I think my question is about the reconstruction of carbonate pump or so-called hard tissue pump, especially for those 200 million years ago when there's little or even no pelagic calcifiers in the ocean like planktonic foraminifera or coccoliths. And I wonder, how do you specify this difference in the CESM? Do you just put, let's say, the ratio of expert of calcium carbonates to 0, like many other models do nowadays?
That is a great question. I'm not very well knowledgeable in that area, but what I will say is that when we are comparing like isotope-enabled CESM output with something like foraminifera, the only thing we simulate is the seawater isotopic composition. So usually it takes what's called a proxy system model as sort of a conduit between what the seawater isotopic composition is and the foram. And those kind of processes come into play in the proxy system model. Yeah.
Just a follow-up question. Is this seawater oxygen isotope constant?
No.
During the modeling? Because
Yeah.
like freshwater flux or precipitations, anything can change that. Do you still use the -1 for most of the case? Or
No, good question. So we will initialize based on so I was kind of talking about on this slide, we know global ice volume is really important for setting like the mean seawater delta 18O value. So we might initialize the case using like a uniform value of something like -1, depending on the climate state, but then it spins up with every other tracer in the model. And so by the end state, we have a field that looks like this, where precipitation and evaporation have influenced the composition of the ocean. The ocean circulation has pushed around the isotopes and modified the composition, and we have like runoff running into the ocean with a certain isotopic composition, depending on the upstream water. So all of that's taken into account throughout the simulation.
Yeah.
Have those adjustments of the parameterizations carried through to CSM3?
Oh, another thing I forgot to say. Great. Yeah, so what I wanted to mention on this slide was that this was all done with CSM2, and a lot of changes have happened to CSM3. So you can't necessarily take an adjustment and go from CAM6 to CAM7, for instance. And so what we're doing is before the release of CSM3, we're running LGM and Eocene simulations with the development code and seeing, do we get something reasonable before the scientific release? So it's been sort of incorporated in the development cycle.
So they are a really cool presentation. I was wondering if you could talk a little bit about what the process of fixing parameterizations are for like different climate states, because like I understand that it might be iterative, but how do you choose what is a well-balanced parameterization when you have so many end-member climate states to think about?
Yeah. So in this scenario, well, first of all, it takes someone like Jungsu to do it. And so the first step of this was saying, let's remove an entire parameterization from CAM6 and restore it to CAM5. Because we know CAM5 is working. And so he took the entire ice nucleation scheme, for instance, and replaced it back with CAM5. So that's the first step. And then he looks at the sensitivity of replacing the parameterization. Once he isolates a single parameterization that's the leading predictor of the temperature trend, then he goes in and starts doing parameter sensitivities within the parameterization so that he can go back to CAM6 and actually make that exact adjustment, if that makes sense.
And that's for one climate state. How do you do that? Like, how do you make it balance between two end members?
A lot of simulations, a lot of, he's running dozens of sensitivities with various combinations of kind of a manual, and he's also done a PPE. So I will say he's done the perturbed parameter ensemble with CAM so that he can narrow down which parameters are the most sensitive in terms of temperature. So that I should mention that the perturbed parameter ensemble is kind of helps you narrow down which parameters, because there are dozens, that will make the largest impact in each parameterization.
It's a painful process for sure. I guess this isn't really a question, but it's something you can comment on. I think something that haunts me a little bit is parameterizing models based on proxy estimates, but then your proxy estimates would change based on the underlying model configuration if you actually factored it into your, like if you estimated temperature based on, let's say, changing delta O18 of the surface ocean that you've estimated with CESM, maybe your estimate of temperature would be different.
Yes.
Then,
Yes.
like it feels very circular.
Sure.
So I'm wondering, like, what, if you could comment on what you think, let's say, you're reconstructing past isotopes in precipitation or something like that. Would you rely on the model to, like, estimate underlying delta O18 of the surface ocean and how that should factor into your estimates of delta O18 of precipitation? Or would you not do that? Like, how should these two fields be talking to each other in terms of making estimates of past climate states?
Yes. What I will say on your first point about kind of the circular nature of it, right, is you are taking, in theory, you could take information from ICSM to calculate the proxy-based temperature, right? But when we get to this step, we're not only gonna take delta 18O based temperature reconstruction. We're gonna want several independent methods of reconstructing temperature and take all of that into account in this spread, so that it's not just the like modeled climate state dependent proxy calculations that are going into the proxy model comparison, if that makes sense. So that should always be included, I think, or many independent estimates of temperature. And then your second point, can you repeat the second part about precip?
So, yeah, so I work on like reconstruction of past delta D or delta 18O of precipitation. And we think about things like moisture source region and about underlying changes in delta 18 of the surface ocean as a source of moisture. Some people apply like an ice volume correction and some people don't. And some people think about things like how the delta 18 of the surface ocean would actually change in different locations in different ways. So like how would you make that correction? Or like do you think people should rely on model output data to inform those types of?
I think because I'm a modeler, I'm always about comparing across as many different scenarios as you can. So for instance, like when we think about isotope-enabled simulations where they're treating seawater delta 18O, a lot of times, like you could take, so maybe step back one. There are gonna be a limited available set of isotope-enabled simulations for you to use for whatever time period you're interested in estimating precip delta 18O when you wanna know, like, I guess evaporative source water, delta 18O essentially. And so I think it's a great idea to use as many as you can, and then also compare that with the more idealized approach of just considering ice volume and what a mean value would be. And it's an ongoing issue. I know there's a lot, even the fact of having a sea surface with varying isotopic composition is kind of unique in isotope-enabled simulation. So it's, you're kind of highlighting an issue that persists. So I don't have a great answer, but comparing a lot of different methods would be my advice.
Okay, great. Let's thank Sophia again. Okay, I'll just do a quick lab check-in. I'm curious, because this morning I think there was some confusion. People don't know what to do with the diagnostics. So once you log into the Jupyter Hub, you just go through the notebook, take a look at the code, and click it through, and you're done. Yes, so that's the intended way of learning it, but be sure to look at the code, and if you want to do your own coding, you could do that as well. So I was curious, most of us were able to log into Jupyter Hub, right? Okay, so this afternoon, because we'll have to log into the Jupyter Hub again, we'll have to do the wave start, as this morning. So we'll do like one section at a time again. And then when you log into the Jupyter Hub, you'll notice a very bottom of your login page, you can select the time, right? The default is 2 hours, meaning you reserve, once you log in, reserve this resource for 2 hours. So if you think you want to use it for longer, you can extend it so that it doesn't kick you out in the middle of your run. So if you think, you had finished your most interested area, you could take a look at other areas, the atmosphere, ocean, land, and sea ice and everything. And to have fun with it. Another thing I want to say is that some people are asking if there's hot water and snacks. They will be, again, provided in the Damon room. So please feel free to grab some snack, have some hot tea and coffee in there. So I think that's the only thing. Almost 3, okay, that's good. So let's now go to the lab and be back at 4:20 again.